we all coming from? This is a New England conference, and so my guess is that a lot of people are just coming across the street here from Boston. I see a lot of Boston faces. I see some of our friends from BU just arrived, and some other folks. So if you're from Boston, will you just stand up? I'm just, like, the city of Boston. Cambridge doesn't count. There's a lot of Cantabrigians here. Okay, who's from Boston here? Okay, great. Okay. All right, that's great. A nice Boston contingent. Okay, Cambridge folks, other people from Massachusetts, you know, Amherst, other folks. Okay, who's here from Massachusetts? Wonderful. So Boston, Massachusetts, I feel like, okay. So now we named the conference New England. So do we have New England people, broadly speaking? Like, did we have any folks coming here from Brown or other folks, placed in other parts of New England? A few New England folks? Oh, yeah, okay. Well, you can stand up. You know, Rhode Island counts. Yay, New England. Okay, wonderful. Okay, great. And then, are there people here from further afield, other places in the United States? Anybody who got on a plane to get here? Who like came from other parts of the United States? Oh my gosh. Do I see California? Do I see Texas? All right. Okay. Yes. Other states. Wonderful. Thank you. And then international. Do we have any international folks here? Wow. People from far time zones. Incredible. So this is, you know, to me, you know, I'd like to take credit for this. But okay, so we've got, I think that we happen to be this interesting time in the field. We're getting a lot of interest, increasing interest in AI interpretability. So first, I want to thank Goodfire for sponsoring this event. As it's grown, it's taken a bit of money to pay for, you know, food and things like this. And so thank you very much, Goodfire. Actually, I think there's a lot of Goodfire scientists who are here today. And so thank you for coming as well. But I think this is one of the pieces of evidence of increased interest in this dream of being able to look at neural networks at large-scale AI and understand what's going on. We've got some startups who are focused on this. Who read this blog post from Dario, you know, not too long ago, and I think that part of what's driving this is both this urgency and this sort of feeling of optimism that maybe we'll be able to actually do it. Maybe we'll actually be able to understand these systems. And I think a lot of the people in the room can kind of sympathize with this. You know, the way I look at it is you know, I don't know what your experience is when you crack open these pre-trained large-scale AIs and look inside, but this is the feeling that I get when I do, which is that, you know, it's kind of like the feeling that Robert Hooke must have felt when he looked under some plants using an early microscope, right? He didn't quite understand what was going on in there, but there's no question there's an amazing amount of structure, right? There's a lot of structure in here. It's doing something. And so the question is, you know, is this clue, is this structure really a microscope into cognition? Can we make sense of it? And I think that we need to recognize that that there's some skepticism in some circles that this is a useful exercise. You know, the counterpoint to Dario's optimism, I think, is an unspoken skepticism in our field about whether it's going to even be possible to understand high-level behaviors from looking at these low-level pieces that we tend to stare at. And so what I'd like to do just for a moment is to recall the path that biology took. And there's a lot of interesting stories from biology, but I think that we're sort of at this moment that reminds me of the 1800s in biology. The ascendant theory, the dominant theory, was Darwin, who pretty quickly was widely celebrated as explaining how new species emerge through natural selection. And I see this as very analogous to our discovery of the power of machine learning, how through kind of a process of evolution, you can really get complex behaviors to emerge. And now the funny thing is, who has heard of Darwin's theory of the gene? Anybody heard of this? He had this Gemules theory, which was, he knew that he needed some kind of mechanism that, that drove inheritance and evolution. But his general theory was actually, it turns out, it was totally off base. He had no idea what was going on. But he was such a preeminent scientist that this really dominated the conversation of what was going on. Meanwhile, almost at the same time, there's this prickly fellow, this friar in Austria, Gregor Mendel, who had been, he was a real nerd. He cataloged 30,000 different pea plants, and he had, established this other theory of what was going on. And he was like, I don't think that Darwin has it right. I don't believe in his gem rules at all. It's like doesn't agree with my experiments. But the interesting thing that I think is, as much of a genius as he was, his work was driven by this scientific curiosity, but it was largely ignored. He sent a copy of his great work to Darwin, where later on it was found on Darwin's bookshelf, still in its wax seal, never opened, never read, right, for 35 years, until it was this was rediscovered in 1900 by a few different scientists who later on celebrated Mendel's early work. But I think that we're at a similar time when people understand that there must be some mechanism. We're in a hunt for the right abstractions. We can't figure out what's going on, and so part of what I encourage you all to do is to be open-minded, and let's not ignore the right theory for 35 years. The right theory may be somewhere in this room. Maybe it's in multiple places. And so the point of this conference is to meet new people and to learn new things. And so to sort of emphasize the diversity of different perspectives here, I'm just sort of listing out some of the posters that we've got here today and the areas that people are looking from: the physics of learning, computer vision, interpretability, biological models, which I think is really interesting, reasoning about morals, morality, moral reasoning, security questions. There's feature analysis, looking at things at the level of circuits and attention, reasoning, in-context learning, the linguistic view, the view that it's important to steer and control these models, tool building approaches. We even have people looking at music and audio, and the neuroscience-inspired view is key. So use this opportunity. The main goal that I have for you all at this conference is to meet new people that you haven't met before and to learn something new. And thank you very much for coming today. So we have a lot in store here, and so I'm going to turn it over to Koyena, who will talk about the program for the rest of the day.
Thank you, David. And so for the agenda for today, we have a lot packed. We have a couple of keynote speakers, talks, and then as you can see, you're all in like different tables with different topics. We have some mediated roundtable sessions and the poster sessions. We intended for just one, but we now have two poster sessions, one in the morning at 11:45 to 1 p.m. So a couple of you guys have already set up the posters. That's great, but you can also set up right now if you want to. And then in the afternoon slot, this will be like kind of during like lunch a little after that at 1:45 p.m. You guys can like start setting up your posters. And then we are hoping to have like group photos like from 1:15, 1:25 around then. So if you want to be in the group photo, feel free to just be over here and we'll take one. And in terms of like the round tables, these are essentially the topics around the tables, around this hall, and you're welcome to kind of like switch around if you're interested in like multiple different topics, and yeah. And now I would like to welcome our opening keynote speaker, Sharkey. And so Lee is a principal investigator at Good Fire, where his team works on developing new interpretability methods. His previous work includes attribution-based parameter decomposition and sparse autoencoders as a solution to superposition. Prior to Good Fire, Lee co-founded Apollo Research and led the interpretability team here. And now we are going to have him talk about NNterp and where we should go from here. Thank you.
Great, thanks so much, Koyena. Yeah, I'm actually not. I've kind of duped you here. I'm going to talk about something else. And David's talk really, set us up nicely for this. So what I'm going to talk about is an idea that's really at the center of our field. Does this work? No. Cool, yeah. This is the idea of features. Features are something that we have put at the center of many of the ways that we think about mechanistic interpretability. There's work here that looks at, features that do X or Y, and features that, where we're using features for steering, or we're, building methods that group features together and explain how different, computations happen using them. But whenever you, get down to it, no one can really give a very precise definition for what a feature actually is. And I think this is a bit of a problem for a field such as ours, because whenever I think of past examples in fields where we were kind of confused about core objects, it didn't really bode well for, it was like a pretty clear sign that we weren't thinking about something, we weren't thinking about things more generally, very clearly. This core object is kind of a sign that the rest of our thinking is kind of confused. And these are some examples, but David brought up the Darwin's theory of blending gemmules. This is yet another example. And I think we should really prioritize resolving this confusion. I think that this will add, a lot of clarity to our work more broadly. And yeah, so I think in order to do this, what I want to do is just give a recap of the standard account of features, and yeah, just highlight what's confusing about it, and maybe then muse on how we might resolve it. I don't pretend to have the correct answer here, but just I'll share some of my thinking on it. So the standard account then is that we have these. Whenever we look inside neural networks, we see what we're calling representations, and these are supposed to correspond to directions in activation space, and different directions seem to mean different things, and generally magnitude seems to correspond to something like intensity or confidence of that semantic meaning being present in the input, and the story goes that we have more features than we have neurons. This is the idea of superposition, and this is why we need special methods to take these features out of superposition, such as sparse autoencoders. And the story goes that we have these features that lie, they lie on different levels of abstraction. And how do we get from one level to abstraction from one to another? Well, we need to do some sort of computation with these features. And so the idea then is that we identify these features, we identify the computations that produce them, and then the idea would be then that we can use this to understand the model as a whole. But again, we haven't defined what the feature actually is. One thing that you might say is, well, a feature can be any arbitrary direction. This, of course, doesn't really work. Some directions may be polysemantic, such as this one here, which seems to correspond to a bunch of different concepts. So, maybe we can just choose directions that are interpretable. Well, this kind of precludes us finding new things out about neural networks. And these neural networks, we expect to know different things from what humans know. And so we don't want to just we don't want to base our definition on what we already know. It's, even if we find, features that have particular meanings, well, there's many different ways to be interpretable as well. There's many different. These are actually randomly chosen directions in a neural network, and yet they are kind of interpretable. And so we don't just get to choose any interpretations. So other definitions we might choose are a property of the input that a large enough neural network will dedicate a neuron to representing. And it's kind of unclear why we would choose this. It's a somewhat circular definition in terms of defining representations in neural networks in terms of other neural networks. So there's some problems there. maybe another definition might be, a property of the input that activates a particular SAE latent. And this doesn't really work out either. Why? Because, well, there's a few different issues. We find that some of these features lie on manifolds, and SAEs just aren't really suited to finding, the fundamental axes of these manifolds. We find that these manifolds being continuous, you can just add more and more SAE features and approximate this manifold in a finer and finer grained way. And you're not really getting at the fundamental, fundamental thing here. We were supposed to, find the fundamental unit of neural networks, and this is just not really finding it for us. Another issue as well is that whenever we look at these features that we've identified using SAEs, there seems to be, similar features seem to point in similar directions. And this should be a pretty surprising observation if we thought that features that we were finding using SAEs were a fundamental unit of computations. What this is suggesting is that there's some sort of underlying computational structure to these features. And so I'm going to later argue that maybe this is suggestive that we should look at computations instead as a primary basis. But our problems don't stop there. There's confusion around if features can kind of span multiple layers, how can we reason about this when they're kind of now in the input and output space of each of our computational steps in each of the layers? Do we permit nonlinear features? It may be the case that there's some nice, there's some very strong structure that we can find in activations, but it may not necessarily be linearly represented, and neural networks can do nonlinear computations. And so are we permitting of nonlinear representations as well? What about attention? Are there things, is an induction head a feature? Not really. It kind of like operates on a bunch of different representations at the same time. Maybe it's better thought of maybe as a computational step. Which is, is suggestive. Maybe should we think of features as computations or representations? How should we, going further on attention? How should we think of features distributed across attention heads? There's basically a lot of confusion here, and I think it should be a priority for us to resolve this, because I do think it sits at the center of many of our confusions in the field. And so, taking a step back, what should we do? So there are some properties, I think, some questions that we should ask ourselves, and that will, I think, help us resolve some of these confusions. Just getting clarity on what type of objects we're looking for, where should we look for them, and what kind of properties they should have, and then look at the methods that we might use then to find them. And so, just very simply, like, what really do we want? We basically want to explain what is going on inside neural networks. We want some way to reverse engineer them. And I think we therefore, just stated simply, like, we want objects that we can use in these explanations. And explanations ultimately are mental models and so we should prefer, some models are better than others, and we should therefore just use, well characterized like model selection principles. And so one of these that I like to use, and others too, is this minimum description length principle, otherwise known as Occam's razor. This is just one of these. This is an example of just a model selection method that we may use to choose some models over others. So with this stated somewhat simply, then where should we look for these objects? Where should we look for these things that we want to use in our explanations? And fine, we can look at activations, but I've covered some of the issues that we've encountered when looking for them here. There's this structure in activations that isn't necessarily used by the network as well. We can find more and more features if we increase the size of our SAE, for example, and find just finer and finer grained features. And there has to be some point at which the network just doesn't really care about these, these fine-grained details that we're finding in this, potentially extremely large SAEs applied to a potentially small model. There's structure that it may just not use. And so we want something that is telling us like what actually is the network doing. What actually is it using? And so for that, we kind of need to look toward computations. And I've also mentioned, this this idea that the geometry of features is suggestive of some underlying computational structure that is giving semantics to these features. And so, I think then this is suggestive that we should look toward computations or transformations. But these are fundamentally continuous. How should we think about chunking them up into things that we can think about individually? And just a simple reframing of how we might think of computations is that it's just little chunks of causality. Algorithms are just little causal steps, and if we can chunk the causal steps in neural networks, maybe we can then find something that we can call the computations that it is that it's doing. And so, you might ask, well, aren't we kind of already chunking the causal steps in neural networks by applying SAEs to them, or transcoders, or other approaches? Kind of, but not exactly. We're chunking them up, and this has an effect on this is kind of chunking the causality to some extent, but it's not necessarily carving the causality at its joints per se. We want some way to do that. And so, there are research agendas that have been ahead of the curve on this kind of idea. There are, causal abstraction is fundamentally like a way to chunk up the causality that, neural networks are implementing into larger causal steps. Singular learning theory, if you squint really hard, is also a kind of like approach that looks at perturbations to the data distribution and looks at invariances in the structures that are implemented in the parameters of the resulting network. The singular learning theorists will have to forgive me for butchering that, but I of course have my favorite approach, but I'm not saying that this is like the only approach. But one of the ways that we think about our work is actually like chunking the causality of neural networks, where you can frame some of our work, which is stochastic parameter decomposition, as doing this, where suppose you want to decompose your neural network into a sum of vectors in parameter space that all sum up to the parameters of the original model. You can, for every data point, you can say, well, each of these terms in the sum, how much, what was their causal importance for explaining the output? Like how much can we, what is their causal attribution? And like one way of thinking about this whole line of work is that we're basically finding a way such that we can, basically split up these vectors of causal attributions such that they're as sparse as possible over the data set. And whenever you do this, you can, our previous work showed that we can break apart, computations that operate on features in superposition, but also we can, some unpublished work that we have, suggests that this can identify other steps that we might, think of as somewhat fundamental steps in neural computation, such as induction heads, or we can also, identify like interpretable feature-like components in small language models. And so, like, some of you may be asking, well, sure, we can decompose our models into these computational steps, but we still need to have these representations. What are we going to do without representations? And I kind of agree with that. Fodor famously said that there was no computation without representation, and I think this is the kind of perspective that has led us toward our current approach to NNterp, where we aim to identify these variables that go into the computations and understand the circuits and to understand the model, but I don't think we have to do it that way. I think we can have representations that are tacit, representations that are defined by what they do in the model. And so that if I were to reframe this, I might say that we should identify the mechanisms and then identify the tacit representations that they're operating on in order then to understand the model. And so this is suggestive of a way to think about features that they're things that are operated on by specific causal mechanisms. Now, I'm not saying that this is the definition, but this is just at least how I think about it. And so, just to finish up, then, I think that these are ultimately problems that we have been grappling with as a field for a short period of time, but they're ultimately based in I think confusions that other fields have bumped into. In particular, cognitive philosophy and computational neuroscience, I think, have lots of lessons that we have, stepped over accidentally in NNterp. And I think we, ignore this prior thinking at our peril, and I think, we can move faster if we engage with these fields a bit more deeply. Cool. Thank you very much.
Thank you. Does anyone have any questions?
Naomi?
Okay, I have a couple of questions that I'm going to try not to make into comments. Sorry. It's so first, in terms of causal sort of signal flow, let's say, something I've been seeing in a lot of causal methods is I don't necessarily see how they're finding the interesting features if we assume that there are that some things are happening just to propagate signal further along the model that isn't transforming it into something new, that's not a meaningful mechanism and is sort of just propagating signals, maybe rotating something, And I wonder, do you have thoughts on how to make sure that we're finding sort of the interesting mechanisms rather than direct propagating of surface level features, and maybe even sort of reproducing some of the issues with non-causal methods where you're basically running a compressor? I mean, you're talking about these MDL bias, preference for MDL on the interpreter, but we're basically running a compressor on a compressor, which is the original language model or whatever we're analyzing, right? So I guess I want to know, how do you think we can avoid restating the simplest sort of operations in terms of just pipeline pushing along the regularities that are at the surface level of the data?
Mm-hmm. Yeah. So I view my job as trying to reverse engineer what a given neural network is doing. And to some extent, to the extent that it is just doing this pipeline, where it's not necessarily doing very much interesting to it, I view it as, my job to identify, fine, this is a step that it is doing. It may not be super interesting, but I don't necessarily want to ignore it or something like this. We do definitely need steps to separate out the interesting ones from the non-interesting ones. But I don't necessarily view this as, at least for the work that I've been doing, it's not necessarily the focus right now. But it is ultimately a thing that neural networks will do, and we should identify just what's actually the interesting parts. But yeah, I guess, at least in, say, transformers, it does feel, anything with a residual stream, it does feel like they can kind of, I don't know, we should expect not a huge amount of this, but maybe you're saying different things. I don't know.
Maybe I can clarify, sorry. I guess what I'm saying is, if you were to run your compressor interpreter model on a fairly straightforward representation of the input data without 16 layers, 30 without 50 billion parameters, 500 billion parameters sitting between you, would you find the exact same connections and the exact same regularities, and it's just that the model happens to pick those up immediately because they're at the surface level, and then you continue to pick them up at each layer as it sort of pipes them along. And so I'm wondering whether I guess it sounds like you think that this might not be a problem because you think that the pipeline that propagates these surface level regularities is still something that's important to understand. I'm just wondering if you think it's a problem that we might struggle to find mechanisms doing anything other than sort of passing along surface level regularities.
Yeah, I think it's possible that, yeah, we are just finding boring things in there. But to the extent that there is interesting things in there, I think the methods that at least, I can't speak to other methods, but the methods that I'm most familiar with, I think they're basically identifying computations rather than, and these computations may be simple transformations, but if there's any nonlinear stuff going on there, it should separate that out as well, because whenever it is using, I think of sometimes I think of nonlinear computations as doing different types of linear transformations, and if you can throw away most of these linear transformations and only do one of these linear transformations, such as a ReLU that's above threshold, rather than everything that's below threshold, then I think you can. I think the methods that at least I'm used to dealing with should identify those. But fine, it will also identify the more boring stuff as well. But yeah, that's not necessarily, at least the stuff that I'm working on, what it's designed to do. But yeah, it's a good question.
Thank you. Hi, sorry, before we introduce our next speaker, I just want to say for keynotes, we're kind of giving like 15 minutes talking, 5 minutes questions, and for students, 7 minutes speaking and like 3 minutes questions. And so, yeah, but thank you for all the questions, and it's all right. Thank you for all the questions, and let's keep it going. So yeah, up next we have Amil Dravid from UC Berkeley. He's a PhD student, and he's a student speaker.
Yeah, thanks to organizers for setting up such a wonderful workshop. Today, I'll be discussing a surprising yet apparently universal phenomenon in transformers with a particular case study in vision transformers. And this is joint work with Nick, Alyosha, and Yossi. So our title here is a bit tongue-in-cheek because the iClear best paper from 2024 was that vision transformers need registers. And they found this very interesting finding that as you scale up VITs, some tokens in seemingly random places get these very high norms. And this bleeds into the attention maps, giving us very noisy, non-object-centric attention maps. And the proposed solution was to basically augment your transformer with these so-called learnable register tokens with the hope that they would absorb these outliers. And this gives us clean internal features and improves some downstream tasks. And as you can see to the right, qualitatively, once we add these, retrain our models with these registers, we get nice clean attention maps. And a similar phenomenon has also been observed in large language models. For instance, Detmers et al. Found that as you scale language models, at a particular scale, these outlier features emerge and naive quantization methods fail. And similarly, Xiao et al. Found a so-called attention sink where the first token or seemingly random tokens get all of the attention as you go deeper into language models. And this has implications if you want to use your language model in a streaming setting. And this is such an issue that even if you look at the GPT open source models, we see that they have learnable sinks or registers. So in our work here, we want to understand how these high norm tokens even emerge in the first place. So we start off by taking OpenClip and tracking the max norm of tokens in the residual stream after each component. And we observe that in the layer 6 after the MLP, we see this phase shift where some tokens get very high norms, and then subsequently we see that the attention scores suddenly rise, indicating an attention sink. So it seems that the MLPs might be correlated with causing the high norms. So let's actually look at the neurons. And by neurons, I refer to the post-nonlinearity single-channel activations. Here we have an image and then the output patch norms, and we see that a very small set, maybe only 10 out of 40,000 neurons, just happen to be activating on where these outlier tokens will eventually occur. So this leads to our hypothesis that perhaps it's the neurons, so-called register neurons, which are creating these outliers. And how we find these neurons is we'll feed in a bunch of inputs, we'll take the norm at the output and then identify our outliers, and then essentially just cache all of our activations and correlate these activations with where the outliers are. And if we take a look at the attention maps at the output, here we see our outliers. So far everything we've seen is purely correlational. So what we can actually do is intervene upon these register neurons, shift them into any arbitrary position very early on in the computation of the model, and then we see at the output the same pattern emerges, indicating this is not purely correlational. We can induce some particular behavior by intervening upon these neurons. So then why don't we just move these tokens outside of the image into a so-called test time register, which is essentially a dummy token. So what we do is we'll do our typical patch embed, which is equivalent to tokenization in the LLM world. We'll feed through, and then we'll basically shift our max activation into this dummy token, zero out our map, and then proceed with the computation. And why do we even need test time registers? Why can't we just zero out the neuron? Well, it turns out that it's an indispensable term inside the model's internal computation. If we zero out, we just destroy the performance. Whereas if we ablate random neurons, we see a marginal difference in performance. So these outlier activations need to appear somewhere inside the model's computation. So here we see qualitatively nice attention maps, which improve our segmentation. And here we can improve on some dense prediction tasks which rely on smooth internal features. And this is another task where you can localize objects. And finally, we can retrofit any model with these test time registers. We don't have to retrain a model with learnable tokens. So here we can add some test time registers to the vision encoder for VLM, and we get much nicer text-to-vision attribution. So in summary, we found a really sparse set of neurons which explain the main mechanism behind registered tokens and outliers. And we can use this to intervene during the forward pass and mimic the role of these learned registers. And then kind of related to the previous talk, here we see that not all neurons have some feature-related role. Typically we think of a sentiment neuron or some object detector. But here we see these neurons are responsible for an image-independent role, which is igniting high norm tokens. So please visit the poster session 2. So far I explained how these high norm tokens emerge, and we have some theory of why these occur, and then I'd love to chat more about this topic. Thank you.
All right, so we got 1 minute for questions. So anyone have a question?
I'm curious if there's a relationship between these outliers and adversarial examples.
Yes, that's a good example. So basically, I guess if you train with some Lipschitz regularization, there would be some relationship. Maybe it will mitigate these. So I guess there is some relationship in that regard. Also, we actually show some applications to some adversarial examples that, so please stop by the poster. Yeah.
Thank you, Amil. And up next, we have Andrew Lee, who's a postdoc at Howard, and his topic is shared global and local geometry of language model embeddings.
Thank you. Hi, everyone. My name's Andrew. Before I start, I want to say thank you to our organizers. And today I'm going to be talking about shared global and local structures that can be found across language models. In particular, there's a growing line of work that suggests that our contemporary models are converging in terms of their representations. But most of these studies have been across modalities. And in this work, we focus on across language models. And in particular, we focus our study on the embedding and unembedding weights of the model. So these are just the weights. We're not looking at any forward passes. And we study models within the same family, and we study 3 different families, GPT-2, Llama 3, and Gemma 2. And in the next 7 minutes, I'm going to speed through all the sorts of shared global or local geometric structures that you can find across these models. And I will conclude by demonstrating a very simple application that you can build on top of these insights. So starting with global geometry, the idea here is very simple, where given your token embeddings, we can first construct this V by V distance matrix, V being your model's vocabulary size, where each entry in your distance matrix D is capturing pairwise cosine similarity scores of each token embedding. And so I think of this D matrix as kind of capturing the relative orientations of your token embeddings amongst each other. And once you have these D matrices for different language models, you just have to compare how similar they are using Pearson correlation scores. And so in the case of GPT-2, you see very high Pearson correlation scores between, say, GPT-2 small, medium large, and X large. But if you repeat this experiment on, say, Llama 3, you actually don't see high Pearson correlation scores. And it turns out the reason for this is because these models with very low Pearson correlation scores have untied embeddings, by which people mean like the model is learning separate weights for the embedding portion and the unembedding portion. So if we repeat this experiment for the unembedding weights of Llama 3, then you actually see very high Pearson correlations. So this covers the global geometry across language models. Now if we were to shift gears to local geometry, we characterize local geometry 2 ways. One is what's called locally linear embeddings, or LLEs, and the other is intrinsic dimensions. First, the idea behind LLE is very simple. What we do is, for every token embedding, we look at its k nearest neighbors, and we reconstruct this token embedding as a weighted sum of its k nearest neighbors. And so that's this W vector here. This is going to be a v-dimensional vector that's very sparse, because only k entries actually are non-zero. And I think of these W vectors as capturing the local structure around each token embedding. And so once you compute for these W vectors for all of your token embeddings, and once you do this for, say, 2 language models, then you can compare how similar these W vectors are. And these are our results, where each subplot here is comparing across 2 different language models. The x-axis being cosine similarity scores, and the y-axis indicating the percentage of the W vectors that have a certain cosine similarity score according to the x-axis. And you'll notice that most of the density lies above, say, 0.8 or 0.9, indicating that most of these local structures are indeed very similar. What's kind of funny here is that you can notice these spikes at cosine similarity score of zeros. And what we think is happening here is that we think these are what people call undertrained tokens, or AKA glitch tokens. So these are tokens that show up in your tokenizer, but not in your actual pre-training data. So essentially what you're looking at is randomly initialized vectors for these tokens. A second way we can characterize local geometry is by defining a simple measure for intrinsic dimension. And we come up with a very simple way to do this. What we do is, again, for every token embedding, we're going to look at its k nearest neighbors. And we're just going to run PCA on those set of points. And we're just going to count up the number of principal components needed to explain 95% of the variance in that local neighborhood. And we're going to call that number intrinsic dimension. And we actually find an interesting pattern here where So here I have some random tokens sampled from the model. On the left column, I have their intrinsic dimensions. But if you look at tokens with low intrinsic dimensions, you often see that they correspond to semantically coherent clusters, where, for instance, for like the word east, you see nearest neighbors eastern, west, northeast, and so on. Same with Nissan. You see nearest neighbors like Mazda, Hyundai, and so on. Whereas if you looked at tokens with higher intrinsic dimensions, you don't see this semantic coherence anymore, but instead you see other sorts of lexical patterns show up. So for instance, for this token Z, you see other tokens starting with Z show up, like Zag, Zig, and Zipper. Or for this token A show, this seems to be a suffix starting with A, and you see other similar suffixes like acebook, asis, assist, and so on. So we think there's some we think there's more to be done by understanding these intrinsic dimensions. And again, if you compare the distribution of these intrinsic dimensions across language models, they end up looking quite similar. Okay, so let me conclude by demonstrating a very simple application that you can build on top of these insights, where given two language models and a steering vector from, say, your first language model, you can transfer the steering vector to control the second language model. So in this example, imagine you have two language models with different dimensions. Imagine you've extracted some steering vector for, I don't know, toxicity or refusal and so on, whether it's through probing, whether it's through some sort of mean diffing. And because we know that the unembedding spaces are very similar, all you have to do is learn a linear transformation to map the points in your unembedding space from the first model to your second model. And all you have to do here is reapply this linear transformation to your steering vector, and this resulting vector T of V can be used to steer your second language model. And so here are some results. Here, this dashed blue line indicates if you were to extract a steering vector for refusal from Llama 3 8B, and if you were to steer the same 8B model. Whereas the orange and green line are if you were to extract a steering vector from a 1B model or a 3B model, transfer it to your 8B model, and then steer the 8B model. And we test this across multiple concepts in Llama 3. Yeah, in the interest of time, I'll conclude here. Thank you for your attention.
So we have 3 minutes for questions. So, any questions?
Thank you. So, Andrew, why is it that you'd expect that the transformation between the output embeddings is applicable at a deeper layer in the network?
Sorry, you said why we expect the...
Why would the same transformation that works at the output layer...
Yeah. So essentially, like if you consider the... I wish I had a backup slide for this. Essentially, if you consider the eventual prediction that the model makes, it's essentially like the last layer projected through the unembedding weights. And so if you think of that composition, I kind of think of it as a bilinear map where so like essentially if you move in a certain direction in your last hidden layer, you're essentially affecting the logits because you can think of that product as being the logits, producing the logits. And I think it's because one, like the transformer is additive through those residual connections. And so if you affect the layers closer to the last state, then that change you made will propagate through the last layer. And I think that's why it eventually affects your logits and affects what the model predicts. I hope that answered your question. We try to come up with a better explanation in the paper. And yeah. Oh.
Does the intrinsic dimension correspond at all to the breadth or narrowness of the feature cluster that it seems to be representing? Or is it more about the, like, some deeper intrinsic meaning corresponding to the concept?
Whether intrinsic dimensions correlate with
the breadth of the concept in the cluster.
Breadth of the concept. I'm not sure. I think what ultimately determines the intrinsic dimensions are like how... I think it has to do with the correlations that these tokens appear in the training data. And so, like, for instance, in my example, I didn't cover this, but there were examples of numbers like 45, and the nearest neighbors are like 46, 47. And I think same thing with years, like 2016, 2018, they show up together. And I think it's because these tokens often appear in similar contexts. And then in the case of tokens with higher intrinsic dimensions, we often saw suffixes show up. And it kind of makes sense for these suffixes to have more directions to like define itself, because I think these are highly contextual and they show up in more diverse contexts. That's my speculation.
Thank you.
Thank you.
Thank you, Andrew. Yes. Oh, yeah. So up next, we have our keynote speaker, Tamar Shaham. And so Tamar is an incoming assistant professor at the Faculty of Mathematics and Computer Science at Weizmann. She's currently a postdoc at MIT CSAIL under Antonia Toralba's lab. And yeah, if anybody is looking into working on NNterp, which is everyone here, and wants to be mentored, she's hiring students. And so, yeah.
Okay, thanks. Hi, everyone. Very happy to be here today. I have super exciting stuff to show you. And speaking of exciting stuff, this is my son, Boaz. He's going to turn 4 in a few weeks. And in the last couple of months, he's been mastering a new capability, which is interacting with AI models. Now, the most accessible AI model in our house is Google Nest. And, you know, you just have regular conversation with it, for example. Okay, I don't have the audio. Just a second.
Sorry, I'm just going to this because I can't see the thing on top. But
We don't have to do it.
Nothing but Hound Dog.
Hound Dog by Elvis Presley Shore, playing on Spotify.
Why do we have that?
Yeah, turn out it is easier to talk with AI models than showing interaction.
Nothing but Hound Dog.
Hound Dog by Elvis Presley Shore, playing on Spotify.
Great, and then something like this will happen.
Okay, Google.
Okay.
Okay, Google.
You ain't nothing but a hound dog. You're crying all the time. You ain't nothing but a
Almost. It's okay, give it a moment. Yes, okay, you know, interacting with AI models, just regular stuff. What is the weather today? Tell me a story. How can I turn into Spider-Man? You know, stuff that all of us are interested in. But lately, these type of interactions become very sophisticated. And this is something that happened a few weeks ago. It was already quite late at night, definitely after bedtime. And my son Boaz was insisting not to go to bed, something that happens almost every night. And at some point I was like, okay, enough, no more toys for today, we're going to sleep now. And he was so mad that he went to the Google Assistant and said, hey Google, my mom doesn't let me play with my toys. And before I was even able to react, the Google Assistant replied, oh, that sounds very frustrating, but there must be a good reason for that. Maybe you need to do something else now, you want to talk about it, blah, blah, blah. And if you look at it at first, it seems like just the text textbook solution for how to be a good parent, right? But maybe there's more inside. Maybe the AI model actually learned something about the mental state of the user. Maybe it was able to say something about the emotion of my son, or the belief that he thinks it's unfair to stop playing now. And also in the reply, you can see that there is some recognition of the emotional state, and maybe some recognition of the reason that the mom doesn't let the boy play. So the question I want to ask you today is, when we see an AI model reason about a mental state of other, is it just some sort of mimicking of training example? Or does the LLM behind the scene actually learn to apply some logical operation to reason about mental state? And what I want to show you today is, in a very, very simple, much more naive case on a task that is called belief tracking, we found that language models actually implement very well-defined algorithm to solve it. But before talking about belief tracking, I want to talk about how language models actually track information in general. And for that, I want to show you a task called entity tracking. I believe I don't have a lot of time, so let's do it quickly. So the task goes as follows. We have a series of boxes. Each box contains a label, and inside each box, there is an object, and we show this sequence of text to a language model, and then we ask the language model to reason about what's inside a specific box. And we were able to identify the subnetwork that is responsible for this task. It's actually a very small network, but we didn't want to stop there. We also want to analyze what is the functionality that the network implements in order to solve the task. And I want to show you the technique that we used. The idea is, you take one sentence, and you take a specific component inside the subnetwork of the entity tracking. And now you ask yourself, what could be the functionality of that specific component? So I took this component. It's in the position of the box label G in the query sentence, and it's inside layer 15 in Lava 7b, already in kind of like the middle of the model. And I want to start hypothesizing what is a possible explanation for the behavior of that specific unit. So I want to do a trick that David taught me, and I want you guys, the audience, to help me decide what would be a good explanation. So the first hypothesis that we had is that at this point inside the model already knows that Apple is the right answer, and therefore it knows that that particular unit already encodes the value Apple, okay? Who thinks that's a possible explanation for what's going on with that unit? No one? Oh, nice. Okay, good. Okay, here's another hypothesis that we had. Oh, sorry. So how can we validate this hypothesis? If this is indeed correct, if we will take that component and we'll just patch the activation of it to another sequence when Apple doesn't appear, then the correct answer should flip to Apple, okay? Great. Here's another hypothesis that we had. Maybe this unit actually encoded the information saying, look for what's inside box G, okay? And we designed the second sentence such that we have box G and we have pitch inside box G, and if this is correct, then the answer should flip to pitch, okay? Who thinks that the second explanation is correct? Okay, nice. So we designed these two sentences, and we did the experiment, and then we found something else happening, which is lamp, the correct answer in the second sentence, was flipped to bored. Why bored? Do you have any idea? Great, position. There is another explanation that we didn't consider here, which is the unit, this head, actually contain information that tell us where to look inside the sequence, and specifically we know that this information is called ordering ID. It was already found before. It actually tells us to look at the first object in the sequence. Cool, so now we know how language models track information. Let's make stuff a little bit more complicated. How do they track beliefs? And in order to answer that question, we came up with the following data set of short stories, and I'm going to show you one example of such story. So we have Bob and Carla. They both work in a busy restaurant. By the way, I created visualization with DALL-E for this. In order to complete an order, Bob grabs a bottle and fills it with beer, and then Carla grabs a cup and fills it with coffee. And sorry, we also know that Bob can observe Carla's action, but Carla cannot observe Bob's action. And then we ask the language model, what does Bob believe that the cup contains? Okay? So it's a little bit of theory of mind analysis here, because the model needs to understand that Bob can observe Carla's action, and therefore he knows that the cup contains the coffee. Okay, again, let's start with a little bit more simple case where we say to the model that none of them can observe each other. So Bob cannot see Carla, Carla cannot see Bob, and I want to show you the mechanism that the model implements in this case. So we already know that ordering IDs are very important in order to track information, and this is also the case here. So the model at the early layers just start by assigning ordering IDs. We have an ordering IDs in the first sentence for the first character, the first object, and the first state, which is beer here. And then we have a second ordering ID for the second character, the second object, and the second state. Okay, so each important token inside the story get this ordering ID that basically say, I'm the first character, or I'm the second character, I'm the first object, or the second one, and so on and so on. Okay, then something very interesting is happening later in the layers. All these ordering IDs are being transferred to the residual stream of the state, and a copy of the ordering ID of Carla and Cup is being transferred to the question. Later on, the model transfers that to the last token, and then it does something super interesting. It uses the ordering ID as sort of a pointer to the previous ordering IDs in order to find where relevant information is represented, okay? And when it found the previous occurrence of these ordering IDs, it basically brings information from there. We call it a look back, okay? So now it brings the ordering ID of the second state, and it uses it again, actually. It tries to look for where in the sequence there was a mentioning of that ordering ID, and when it finds it, it can bring the token itself, coffee, okay? So we see this repeating mechanism. We call it the look back. Basically, the model split the same type of information, two copies of the same information in two different locations inside the model, such that it can use them as a pointer and a reference and to bring relevant information forward. Let me quickly show you what's happening in the complicated case when we say Bob can observe Carla's action, but Carla cannot observe Bob's actions. In that case, again, we have the ordering IDs, and the model transfer them to the state of each sentence, and also create copies of them in the question sentence. So you can see now, we don't have the same ordering IDs in the question, right? We ask about Bob, what Bob believes the cup contains. And that's why we need the visibility sentence. So in the visibility sentence, we basically have the ordering ID of Bob and Carla, and we have another interesting marker which basically represents the visibility between the observed character and the observing character. Okay, so that visibility ID basically connects between them, such that now the model use another lookback to bring the information about Carla's into the question sentence, okay? And now everything continues as if we were asking about Carla. Okay, it has nothing to do with Bob anymore. So we use the lookback to bring the ordering ID of coffee, and then it used the ordering ID of coffee to bring the value coffee itself. Okay, I don't have a lot of time. There is a lot going on in this paper, and I'm advising you all to talk with Nikhil about it in the poster session. I think it should be here somewhere, Nikhil. Hi. So talk with Nikhil in the poster session. I'll do say that we do believe that this look-back operation is very fundamental in a lot of different tasks, and in fact, we already see preliminary evidence that vision language models use look-back in order to do spatial reasoning. So if you have an image with a few objects and you ask a VLM, for example, what is the fruit to the right of the pineapple, it uses look-back to reason about that spatial orientation. And you can meet Kelly at the poster session to talk with her about that. Okay, I'll use the one last minute to wrap up. So we still have a lot to do in order to be able to analyze this type of cases, which are obviously much more complicated than the belief tracking case I showed you. And I believe that one of the way to do that is to automate the way we do this type of analysis such that we can integrate information across data that is not structured, not templatic, as we are used to right now. And this is something we are actually working on with an interpretability agent. And in fact, we already have a version of interpretability agent that can automate this type of experiments that I showed you in the beginning, where we find that a specific unit is actually encoding a pointer to a specific location. When we ask our interpretability agent to also reason about that case, here is the explanation from the interpretability agent. So you can see that it actually explained that this head provides positional information necessary for predicting the correct item inside the box. So pretty accurate, right? Okay, cool. And Tal was supposed to present this work, but unfortunately she couldn't arrive. She couldn't make it today. So feel free to catch me after the talk. Okay, that's it. Thank you from Bob and Carla. Happy to take questions.
Well, thanks. We have 3 minutes for questions.
Happy to take parenting questions as well.
Hello, thanks. Is it working? Yeah?
Try now?
Oh, okay, thank you. I'm wondering, do you think that like all the alignment pipeline that we run on the model will kind of change the way it represents the user? Because like, so in those like kind of toy tasks, it's mostly used for entity tracking, while because of like all the alignment, the user beliefs becomes like much more important to like ensure that you're helpful, I mean as helpful as you can, etc. Do you think like it will change a lot the way the model represents them?
That's a great question. I'm not sure actually. I guess it really depends on the type of it depends on the type of representation you wish to keep for the user. We don't even know what type of like when we say the model represents the user, we don't even know how it represents the user. So it's hard to tell how much alignment procedures actually change that. But if you do believe that the model actually contains information about the mental state of the user, which I believe is true to some extent, then yeah, obviously alignment could change that. But it's an interesting research question, I guess.
think that's it. Thank you.
Thank you. I think now we have our roundtable discussions. I'm gonna put the screen up online to just show you the discussion topics. But in general, what you wanna do is just chat with people around you. Talk about your interests, how you came into interpretability, what in particular about the topic that you're interested in. And yeah, we will give about 30-ish minutes for that. So yes.
And then each table should have at least one, usually more moderators as well. And otherwise, just you can go to whatever table you want.
Hi, everyone. We're going to start our demonstrations for the NEMI conference. So we have some exciting demonstrations coming this afternoon. We'll be starting first with NDIF and NNsight. That's going to be presented by Jaden and Caden from our from our team at Northeastern University. And then we will have Clément Dumas, who is a math scholar, and he developed the NNterp wrapper for NNsight that has some really cool functionality that he'll walk through. And then we will have the NDIF team present their European version of the National Deep Inference Fabric. And they've run a pilot out of Germany that is bringing LLM serving to the European researchers. All right, so let's get started. First will be the NDIF and NNsight presentations, and this is what we'll discuss. NNsight 0.5, NDIF, some hot swapping, and the Workbench user interface. So, but first, to motivate NDIF and why we're doing this, I want to see you raise your hands. What size models have you researched? Have you researched toy models? Raise your hands. All right, lots of you. Have you researched models around 8 billion parameters? Yeah, cool. 70 billion. Okay, I see hands. A few. Okay, how about greater than 70 billion? Oh, wow. Not too many. And how about 400 or more billion? Yeah, extra lunch. Okay, so I still don't see that many hands. So that's the major motivating reason for our project, is that it's very difficult to research these large-scale AI models, even as we continue scaling. So the National Deep Inference Fabric is a transparent research computing fabric that allows scientists to probe and alter the internals of large-scale AI. So we do this through three major veins. So first is software, which is the NNsight library. It's a transparent AI inference API that Jaden will discuss more. And we also do this through capacity, which is our scientific AI inference service that is served on Delta GPUs. So we are serving large language models and giving them to researchers to study their internals for free. We are also doing education and creating interfaces that Caden will discuss to help interdisciplinary training on these enabled AI methods. So the way this works is that the scientists can get full control of large models. They write some research code in Python using NNsight library. And the NNsight library will actually interface with the hosted models on the NDIF platform. And the researchers can actually send requests to these large models like Llama 405B. I think the people that research Llama 405B may have actually been using this. And then the model will run your request and send back whatever parameters and data from the model that you need. And all you have to do is add remote equals true into your Python code. You don't need a giant GPU or millions of dollars or anything like that. Great. So now I'm going to pass it off to Jaden, who's our principal software engineer, to discuss NSight 0.5.
Thanks, Emma. Some of you may already be familiar with NSight, but if not, I'm going to go through a brief tutorial about just the basics and kind of why it's designed the way it is. Let me switch. Cool. Yeah, so what is NSight? So there are three kind of key reasons why NSight is the way that it is and why we designed it for interpretability. So obviously, it's built around enabling interpretability of like not only 4 or 5 billion size models, but for any models. So you know, interacting with researchers and finding out what their needs are is an important component of development. It should have primitives for complete control of PyTorch models. So like you should be able to define any logic that you want and inject it anywhere in the model in order to do any of the research you'd be wanting to do. And of course, obviously, it's an API for executing interventions in NDIF. So you need some way to be able to define your experiments, and then so we can transfer them to NDIF and execute them remotely. So to describe how NSight works, we're going to go through a very simple example where we're going to run llama 8 billion and generate 1 token of text. And we're going to force 3 specific layer 14 neurons to be on by raising their activations to be pretty high. And we're going to print the generated token to see what the effect of the intervention was. So NSight and NDIF are largely right now for LLMs wrapped around Hugging Face, the actual weights storage, and for their actual API to define like the common interface for LLMs. So like you would with your normal research, you would define the repo ID for which model you want to experiment on. And so here's the key part of NSight to understand actually how we do the interventions and why we wanted to design NSight this way for the remote NDIF aspect. Is we have your interventions as a context. So you want to be able to execute, obviously, a prompt, some execution of your model, and define some logic that you want to execute while the model is running in order to either get activations to see what it's doing or inject your own logic like steering. So instead of maybe a normal line here which would be model parentheses the truth is the execute, instead we're going to execute it as a context manager where we're going to ask NSight to execute the truth is the in the model. But first we're going to define our little experiment here. So one thing NSight adds is a .input and .output attribute on all these different modules, and that's how you say, please grab the input or output of this module while the model is running. Let me just skip ahead a little bit. So to actually do the intervention where we force these neurons to be on, I can just use like normal PyTorch and Python syntax to say, please at this layer 14 MLP down projection, grab the input for me, and then store them in this variable. And then these 3 neurons, I want them to be on, set them to a high activation of 10. One of the researchers, Eric Todd, in our lab, he has research that shows via his function vectors work that these 3 neurons for this model correspond to like the antonym task. So turning these on will actually force the model to think, oh, I'm doing antonyms, I should respond with the opposite of whatever I would normally output. Yep, so in this case, doing this intervention here will force the truth is the to actually predict lie when normally it would say the truth is the truth. So yeah, so in summary, right, we have this context, we grab all your lines of code, and that's where we're placing the PyTorch hooks later down the road to actually do your experiment. Normally you'd have to do the hooks yourself or edit the model's code, which if you forget to remove or do it in the wrong way, it corrupts your results. You might have not noticed until afterward. I've had that happen before. So now we're going to make one tiny change, maybe a large change to that experiment. Is instead we're going to do it on 405B. And so how to do that is, of course, we change what model. But obviously on my machine here or on one of the machines I have at the lab, I can't actually run 405B. But all I have to do, like Emma said, is just switch the remote equals true flag to on, and this will use NDIF and send these 3 lines of code to our remote server to perform the experiment. I didn't run it on 405B, but you guys can try it out yourself. It's probably 3 different neurons, but you just go to get an API key right now, and you could run this or any experiment on 405B. And so at a high level, right, here's how the NNsight NDIF collaboration works, where your research code is being serialized and sent to the remote server, where amongst other people's requests, we're doing all the routing and queuing, and then using NNsight on the remote server to actually perform the interventions and sending back any of the things that you've asked for. Cool. Okay, so new things in NNsight. I'll just quickly talk about this, but it's a complete redesign of how we actually send your interventions, where before, we were tracing your experiment code to produce this intervention graph, where like each operation is a node in a computation graph, which we can serialize and send over. But there's a lot of downsides to doing it this way, because you have to have specific support for all the libraries to actually recognize, what these different objects are. And at the end of the day, what you want to do is you want to just send the code, so we don't have to have any specific logic for dealing with complicated experiments. So now instead we do just-in-time code extraction to actually look at your code textually and just convert it into an actual Python function, which can be serialized as bytes and just sent remotely. So now like anything you want to do in an experiment can be run remotely without any complications. Another really important update is you can intervene anywhere now. So before, and if you use base PyTorch models, one of the limitations of using PyTorch hooks is that you can only interact with the inputs and outputs of modules. But like a common example here is that if you want to access like the attention weights, pre-softmax, there's actually no module like during the attention forward pass for you to do that. And now in the new version of NNsight, there's this .source attribute, just like input and output, where you're saying, I want to access the source code of this forward pass, and then there's a specific variable, which I will show you a little demo of, but now you can access essentially anything in a forward passive model and do the interventions just like you would previously on inputs and outputs. And let me go into that demo now. What time is it? Okay, cool. Yep, so in this demo, I will do this remotely, just it's cooler that way, and I will show you the .source feature. So first, we're just going to print this .source attribute, and what that's going to do is it's going to show me the actual forward pass code of the attention module of the DeepSeek distilled model here. And so now I can see all the different variables that exist during the forward pass of my model, and I can pick out these variable names here, and I can intervene directly on those. So in our case, to get the actual attention weights, it's this attention interface 0 variable. So now I can let this continue to run. This is going to send this request to NDIF, and it's already done. And so here are my attention weights when normally I wouldn't be able to get those. Okay, so now let me talk about what's new on NDIF. Cool. So Emma recently ran a poll to decide like what models we should actually be running on NDIF. And I think when we first started the project, we initially thought that this was a project for the biggest models, like 405B, that nobody could really run. But I think from the past year, we've come across that most people want to run medium-sized models and a lot of different ones, to perform their experiments and do whole, comparisons in their tables for their papers. So there's a big diversity of models people want, different revisions, and so supporting all these different ones. Obviously we can't have every single model in existence running all the time for users to use. So the biggest new feature to NDIF is on-demand hot swapping. So you ask for a model and we deploy it, assuming that there's capacity. And so let me show you the current new NDIF status page. So we have a bunch of models that are pinned and always running for you. But for example, this model here this one only exists because I requested it earlier. And when models are removed for other models, they're actually put on CPU to make future requests to them much faster. So like, for example, this model right here, our llama distilled DeepSeek model is warm, so now when I request it, it's going to be up much faster. And for the second code example, let's do that exactly. So I'm just like before, in my previous example, I'm going to ask for llama distilled instead of Quen with remote equals true. And it might take a second, but it should be up pretty fast. So now, NDIF is going to receive this request and notice that this model isn't up, check to make all of our nodes to make sure we have room, maybe bring down a model if it needs to be, and then deploy our distilled llama 8B, and then run our request. And once it's deployed, it'll be up for as long as you need it, and you can perform, your set of experiments for any model. Nice. Okay, well, I had an error, syntax error at the bottom, but it did run. But hopefully this refreshes, and yep, so now we have llama 8B running, and so you right now could just go on your laptop, go in Collab with no GPU, get an API key for free, and request any of these models that we have currently downloaded. Soon we'll have the ability to literally load any model, just download it for you, but obviously there are some protections that have to be put in place so you can't inject your arbitrary code, which I'm sure you'd want to do. Yeah, and so with NNsight and NDIF, right, you have essentially all of these primitives of how you'd want to interact with any model, any PyTorch model in existence, and then an actual platform to run on any of these models you want to experiment on. But the ultimate goal is to have these abstractions on top of that and all these applications using NNsight and NDIF as a backend in order to make research easier and more streamlined. So Caden's up next, and he's going to show you a demo of his Logit Lens Workbench, which uses NNsight and NDIF in the backend to have a Logit Lens interactive workbench that you can look at results and do your experiments there.
Thanks. Okay. Hey, so today I'll be presenting the Logit Lens Workbench. Let me see if we have the slide here. So you can follow along my presentation by just visiting workbench.ndif.us, and this should automatically bring you to a login page. And if we go here, let's just sign out. Okay, cool. So continue as a guest, and we can just go through the CAPTCHA. These are some crazy CAPTCHAs. Okay. Oh, fewest holes. I failed it. Why is this CAPTCHA so hard? Wait. Do I have to rotate this? Wait. Oh. Okay, cool. Nice. Okay, so I'm a human. So as a quick background for this, Emma gave some background here, which is we wanted to build an interdisciplinary tool for researchers to share their findings with people who don't have technical experience in coding and other researchers in non-technical fields like psychology or cog-sci who might want to see some of the insights from interpretability. So we started out with the Logit Lens interface, and as a background, Logit Lens is an early exit decoding technique where you can take the final unembed and then decode a hidden state inside of the model at a certain layer and view basically what the model's thinking, or like an early prediction. So I have a couple of prompts over here. We'll copy it with one hand. So let's start simple. The Eiffel Tower is in the city of, and you'll get a basic Logit Lens heat map where along the axes, you have on the y-axis the input tokens and the x-axis the layers. So this is a small model like GPT-2. And we can see that, okay, the model just doesn't know how to do this task. So we can switch it to a slightly larger model like Llama. And this is a great part about NDIF, where we can just switch to any model on demand. And another great part about the interface is that it makes it really easy to do exploratory workflows where maybe you don't want to write all the Logit boilerplate, and you can just write everything up on the interface and then share some of your findings with the reports feature that I'll show in a second. So we have this larger interface for Llama. We can decrease the step size. So Llama actually correctly predicts a token Paris. And we can view the token Paris as a line chart instead, which is just another way to look at specific tokens as the model progresses with its predictions. So this is a simple prompt, but like, what are some of the insights that we can get with Logit Lens? So if we go to create a new lens area, we'll use one of these prompts, which is a multilingual prompt from the paper Do Llamas Work in English by Mueller et al. And if we enter this translation task, where we have the model translate from French to Chinese without any like English intermediate, if we look at the hidden states, we'll actually see that the model does think about an English token in the middle. So it thinks about the token flower kind of weakly here. Let's try a different prompt. Maybe this prompt, which is for the translation from French to Chinese for cloud. And if we paste this in, we can see that we get a really interesting insight into Llama, where we can zoom in on the chart and we'll see that actually the model has a higher probability at an earlier layer for the token cloud, and then this probability decreases towards the final layer where it predicts the right token in Chinese. And if you can go to the actual paper and see a lot of other prompts and a lot of other like closed tasks and language tasks in which the model does the same thing. So now that we have some insights, let's maybe go back to a heat map. We can create a report. We have these great charts and these awesome findings, and we can share it with our colleagues. So we'll have a markdown report. We can drag our charts into the report, and we can share this report with our colleagues. So like we have some, like a heat map here, or maybe a line chart. And anybody can see some of the work that we've done and some of the cool findings that we've made. And it doesn't require them to write a single line of code. But yeah, this is it. And all this is made possible through some really great collaboration with like John, maybe in the audience, and Gwen, and the rest of the NNsight team, and David. So yeah. I'll pass it on to Clément. He'll be talking about NNterp, which is an awesome new library for standardizing interpretability experiments.
Thank you. We just have to switch the computer. Okay. So NNterp is basically just a wrapper around NNsight with like some nice utilities. So if you want to follow along, there is like a demo, a collab that you can run at the same time. And so like the motivation of NNterp is like, just maybe a few questions in the audience. Who has used transformer lens for experiments? Cool, nice. Who knows that transformer lens doesn't really work with the Bloom models? No, you know. So like transformer lens is another great Mechanistic Interpretability library, and it has like, what it does is basically it re-implements the transformer and translates a lot of like famous models like Llama, GPT-2, etc. in this like custom implementations, and that allows them to give you like specific hooks to get like the query vector, the value vector, the attention probabilities, etc. And so then the question is like, why would you use NNsight instead? And the thing is, if you have from a scale from good to bad, which is very big on the screen, relying on custom transformer implementation is like both good and bad. A very fancy graph. So the good thing is that like all your hooks are correct as soon as you program them correctly, and that like also if tomorrow a geek face decide to change the internals of the computations, then your library is not affected by it. So that's the good thing. Then the bad thing is when they train the models, I don't know what they do, but like they have like some very, very specific quirks, very weird quirks, like, oh, you should do the layer norm in float 32 and not bfloat, or you should do this and that. So each model is very different, and if you want to have a unified kind of implementation, then you kind of need like a lot of ifs, and like when a new model comes up, you need to wait for someone to actually sit down and understand what they did. So this can make it like quite difficult to do, and then you don't benefit from like all the optimization people made to make those models run faster. So yeah, there is like a trade-off there. And basically, with NNsight, what you can do is like you can have any hugging face model, but then I don't know what they do when they code those models, but like every model has a different name for the layers. Every model has a different name for the MLP. So like when you want, when the reviewer tells you, can you run from like Gemma to Quen, you might have some like weird surprise where your code breaks in like unexpected ways just because a module has a different name or something. And so an NNterp goal is to ensure you have like a standardized standardized like interface to do NNsight computation with those models. So just like to give like an example, if I have a kernel. Okay, sorry. So like, for example, Llama models are coded in a way that you have the model, then you do dot model, then you do dot layers, then you select your layers, and you can access like with an NNsight you can access the output. But like if you use GPT-2, then now it's like model.transformer.h, dot the layer you want, and so like this makes it like not very easy to like switch from one model to the other. And NNsight has a great new feature that's called rename, and that basically allow you to like rename modules such that, for example, when you want to access the layer module from GPT-2, you can do now like model.model.layers instead of doing transformer.h. So this already like this feature alone, without NNterp, with just this, can allow you to like switch to models more easily. So that's the first thing. Like yeah, one of the things it does that NNterp does is like by default you will use device map auto, which should be the default, and it's not, in my opinion. But like you can always just override it. One other thing that's a bit annoying is if you want to change layer output, currently you have to do like dot output, and you need to take the first element of the tuple, and then you need to change that. And like actually, that doesn't work because it's a tuple. You can change the value of a tuple like this. So you're like, okay, then I will like change this by slicing the tensor. Like that actually works, it's great. But then if you want to use the gradient, it breaks because you did like an in-place operation. So you go, okay, I need to do something else. So now you replace the tuple, which doesn't break the gradient flow. It's great. But on the last layer of some models, if you don't return the cache as like the second element of the tuple, that breaks. Cool. Okay, so now I need to do something else, which is the most robust way in NNsight. I mean, using hugging face transformer implementation to change the layer output is this very ugly line at the bottom. And like no one should have to do this, and NNterp is fighting for this. So with NNterp, what you just have to do, yeah, that's when image generation is quite good. So in NNterp, what you have to do is like if you want to layer 0 output, you can just call dot layers output. And then if you want to change it, you can just use a normal assignment, and under the hood, NNterp will like do the ugly line I've shown above. And actually, there is another thing that you might not know is that in the latest transformer release for Llama model,
they change something in the internal. So no one knows it because when you run the model, it's the same, right? But the layers, they don't return tuples anymore. They return one tensor. So if you upgrade it to the latest transformer version and you run your NNsight code and you do this like you select the first element of the tuple, you're actually intervening only on the first element of your batch. So you just broke your experiment by upgrading transformers. And like Hugging Face is not a Mechanistic library, so they have no incentives to like keep a consistent kind of interface in the internals. And so what does NNterp against that? When you load the model, it will run a series of like tests that will ensure that like everything has the right shape, that like the attention probabilities that you can get already, they do sum to 1, etc. And so like the trade-off for that is that when you load the model, it will be dispatched, so which means it will be like loaded on the GPU, which is not the default with NNsight, but you can disable that. And also attention implementation is set to eager because that's the only way to get to actually be able to like perform edits on the attention probabilities. So yeah, so attention probabilities. So like Jaden showed you like how you can use source, but like you don't want to look at the source code of a Hugging Face model. It's horrible. Don't do that. So I did it for you. I'm still alive. And so now with NNterp, you can just do like dot attention probabilities and the layer you're interested in, and you can both access them and also intervene on them, which which will change the model, and is not as easy as you would think. And so yeah, when you load the model, it will check like that indeed the attention probabilities sum to 1. And then, yeah, also it has a pretty print for, attention to like show you where it takes them in the source code. So that like, no? Okay, anyway, sorry. But like it prints you like, if you execute it in the notebook, it will print you in a markdown format so that like you can see it properly and can verify that the hook makes sense. And then there are a few built-in interventions that are already implemented, like project on the vocabulary. If you want to do logit length, is useful. You can skip layers to like skip the computation of a layer. This can be useful if you want to like run the first forward pass on the 6th first layer, cache the activation, and then if you want to start the computation at the 6th layer, you can just do this. And yeah, that's pretty much it. And like, there is some missing stuff. Like for now, I didn't implement like accessing the queries or accessing the values, but I would really welcome like contribution for this. And I might do it myself in the future. But I think like this gives like a good start of like standardizing everything. And like the thing is, you don't have to use any of this. You can just load with an NNterp and then just use normal NNsight code. Like there is no trade-off regarding this. So yeah, thank you.
All right, we have some time for some questions. So maybe we can bring the NDIF team up here too, and we can do questions for NNterp, NDIF, and Workbench. Yeah? All right. We have until 4 p.m. for questions, so we can also move on if there aren't any, but I would love to hear some questions. Yes. Okay, give me 1 minute. I need to go to the other side. Oh, Koyena's coming. Maybe. Yeah, I'm almost there. Sorry.
Hi, so this is an NNsight question. Would it be possible to support vision language models in the future?
In the NNsight library itself, like which models? Like right now, you should be able to load any language model with any like auto model from Hugging Face.
Like Qwen 2.5 VL. I'm currently using the wrapper, so I'm not sure if I'm loading it like properly. Like I used the NNsight class module wrapper for that model. It works for my application, but I'm not sure if that's the best way of using.
Yeah, you should be able to wrap it in language model or like the base insight class, and like it should work automatically. If it's a model that doesn't use like the normal causal for LM like interface, or like a BERT model or something, you'd have to like pass it a different auto model class, but it should work with anything.
I will. We also have a discourse and Discord community. You can check out our website. It has links for them. And we have some more questions that I'm going to find. But this type of question, like, can you support a vision language model wrapper, could be something you could post on our discourse, and we can have a conversation about it. All right, Eric.
This is for Caden. I'm curious what other no-code interfaces you're thinking about for the future.
Yeah, we have a patching interface in the works, and very prototypey, but what I really want to do is like you can submit a job on NNsight, and you can just pass your job ID to the interface and see some like chart or heat map from your job without ever having to plot anything in Matplot, and then just add everything and drag stuff to reports as well. But yeah, we'll have patching soon.
And we're also, I think, going to be developing a input attribution interface sometime in the next year. And we're hiring Gabriel. Where are you? Yeah. All right, any other questions? Yeah. Oh, great.
So thank you for the presentation. So I was wondering, for the low-code interface, it would be really nice with this report functionality to actually have like the translation into code, because I think it would be very, very good for reproducibility, right? Like to be able to run step by step again the same analysis, right?
Yeah, is if you open on the Workbench, there's a button right now where you can do that, but the code is just like completely wrong, because so don't click it yet. But
right.
There's also a copy chart button as image too. So yeah, you have both those export features as well.
Amazing.
Yeah.
Let's see. Anyone else? Any questions for Clément? We got one. Yes.
Hi. Does NNterp support remote execution on NDIF?
So not yet. So because standardized transformer inherit from language model, and for now NDIF only supports language model directly. But like we're talking with Jaden to implement this in the future, and maybe even merge an NNterp into NNsight to be part of the library. So yeah, so like either it will be just like out of the box available, or otherwise there might be like some like another class like standardized transformer remote that will like handle this. But yeah, the goal is to make it also available via NDIF.
Wonderful.
All right. I think we have one more. We can probably just start. Okay. We have one more demonstration, and very excited to introduce the EDIF team. So a few months ago, we got an email from these people in Germany, and they were like, let's do this in Europe. We love what you're doing. And it's been really exciting. They've created a whole pilot program and ran it in Europe, hosting remote models and building their own infrastructure based on the NDIF infrastructure. And they're going to share about their pilot program and how it worked. So,
yeah, thank you, Emma. Hello, everyone, and thank you for the opportunity to present our study at the NEMI workshop. My name is Sandra, Kalogiannis, and together with my colleague Fabian Maag, we will share our work on the European Deep Inference Fabric, or short EDIF. This project is based at Ansbach University of Applied Sciences in Germany. It was developed in close cooperation with the NDIF team in the US and several other European partners. Today, we will walk you through 3 points. First, why we think Europe needs its own interpretability infrastructure, what we have learned from our feasibility study, and where we see the project going next. So, why Europe? In the US, NDIF has shown what is possible when there's a shared infrastructure for mechanistic interpretability. It offers a common technical foundation for researchers, increases collaboration across institutions, and has boosted the growth of the field. In Europe, the situation is a little bit different. Mechanistic interpretability is still less organized, but some countries stand out already. Some disciplines have a genuine interest in mechanistic interpretability, such as linguistics, neuroscience, psychology, AI ethics, and law, but they often work separately without a shared infrastructure. So our conclusion from this was clear. We want to build on NDIF's proven success and bring its momentum to Europe. We will learn from their experience and strengthen the ties between our communities. This is exactly the vision behind EDIF. But of course, the vision comes with questions. Does Europe already have the necessary foundation to make this happen? Do we have a critical mass of researchers to justify building a European complement to NDIF? And perhaps, most importantly, how do we get everybody on the same boat and ensure we are not just building another silo, but something truly accessible and collaborative? So we framed our vision around connecting disciplines, leveraging Europe's diversity, and using our high-performance computing resources to democratize access. To test this vision, we ran a structured feasibility study. The initial contact with NDIF began when our professor, Sigurd Schacht, representing Koyena, met David Bau at the ICML conference in Vienna in summer 2024. From that, we moved into the technical setup of our cluster in early 2025, followed by a pilot phase in May. During this pilot, we had 16 participants from 7 European countries. They carried out a range of models, from smaller architectures, from smaller architectures up to DeepSeek R170B, all running on our cluster infrastructure. The process included orientation and preparation phase, data analysis and reporting, culminating in July 2025 in our paper. This structured approach allowed us to evaluate both the technical performance of our cluster and its reception among a diverse group of European researchers. And with that, I will now hand over to my colleague Fabian, who will give us a short deep dive into the details of our study.
Right. First of all, thank you, Sandra. Now it's actually starting to be my turn, and I'm going to talk a little bit about a feasibility study that we ran. Now, first of all, let's talk performance and requests. So we handled a maximum of 700 or more requests daily. And we didn't only handle it well, we handled it with minimal errors. Errors as in they might just be attributable to our IT systems and our infrastructure and not even down to NDIF or our EDIF cluster itself. Model-wise, we ran models up to Llama for Maverick, so quite larger models, and we handled them stable. And we didn't even handle them stable, we handled them on AMD GPUs as well, which is, as I've heard, a quick win for the NDIF team as well, as the migration to run just a single model on AMD GPUs required minimal adjustments and was really easy to do for us. But even though this is a nice quick win for us, we still had some problems. One of these problems being, if we have a model that uses a GPU, any bit of memory that this GPU has left is wasted memory. And if you think about sustainability, this is not ideal. And as Jaden has shown you before, hot swapping is a thing that might work for us in this case in order to utilize our GPUs better, but right now we're still handling inefficient models, which is not ideal. But nevertheless, the users out of our feasibility study said they were highly satisfied. Most of them report a lot of time savings, which is really good for us because in the end, we don't want you to participate in a feasibility study in order to spend more time on something, but ideally, we're going to save you a little bit of time and you're going to learn something new, and ideally for us, you will contribute useful feedback. This useful feedback contains, for example, wanting more models, which is kind of easy to do if you have more resources, but they also provided more even useful feedback, and in terms of some of this, Jaden already showed us that some of this has already been taken care of, such as hot swapping. Caden already showed us they're working on low-code, no-code, which we are going to talk about briefly shortly as well. And together, all in all, we can say it has been a pretty big success, even though participant-wise, we've only had a small group of researchers that we selectively handpicked. But this tiny group of researchers resulted in power users who managed to contribute valuable feedback. Now, apart from feedback, I want to talk to you a little bit about something, I'd say, specific for Europe, or for Europeans, or for the European Union itself, because we call ourselves EDIF, but if you think European Union, it sounds like a union. Technical-wise, it's not exactly like that. If we said, okay, our implementation builds on NDIF, we adjusted a few parameters, we maybe put in a reverse proxy, and then we called it a day. Would have been sufficient. But the thing is, what we aim to do is, we want to build a big community in Europe. And we want to build this big community. In order to build this big community, we have to build an infrastructure that is deployable on every single country's sort of compute resources. Like, everybody has to be able to build on this. And in order to do so, we had to basically migrate the entirety of NDIF to high-performance compute cluster-compatible systems. And this includes switching entirely from Docker, which I'm sure 99% of the people in here have heard of, to Aptainer, or formerly known as Singularity. And this basically meant rewriting the entire infrastructure, everything networking-wise, and migrating everything just to Aptainer. Because the thing is, in Europe, everybody more or less does their own thing. There is collaborations, there is cooperation. But in the end, every country has their own guidelines. But something that we did agree on is just that we have high-performance compute clusters, and we need an infrastructure that works on both of those. Now let's talk about what we learned from this. A few key takeaways. First of all, it has to work on everybody's machines, which is what we did accomplish in the end. Second of all, we noticed that we do have great researchers, right? Some of them are even in the room with us today. But there is a reason that we are here in Boston right now, and not somewhere in Europe, because the community in Europe, it's not as consolidated. Like, everybody exists, it's kind of doing their own thing. If we meet, we mostly meet at places like here in the US, where there's bigger conferences, and in the European circle, there's not really this central point, and we want to change that. And we don't only want to change that, but we also want to get more people into the boat. Because the thing is, right now, admittedly, NNterp, I believe we can call ourselves a bubble. Like, it's hard to get into the field. Everybody who started has had, like, more or less difficult way to get into it. I, for myself, struggle a little bit. And I have a little bit of a story about this when I want to talk about community building. Because the university I do my PhD at, we have a psychology professor. And she approached me, hey, Fabian, I heard you do this language model stuff. I have like 2 master's students. I found out that you can do a little bit more than just prompting, which I was surprised anyways to see that, well, a psychology professor who probably written about 10 lines of Python code in her life even heard of this. And then she asked me, can you get me started and brief me a little bit, like a 30-minute Zoom session, so I can get them started into working on this? And I said, okay, let's try it. Trying it did. But in the end, the meeting ended as in, do you have another day of time, like maybe 6 hours, so I can get you started? And to me personally, this was kind of a wake-up call, because what we are doing, unwillingly, we're gatekeeping our field, more or less. And the thing is, if you go back into some older research, like the oldest of researchers, like the best things happen when completely different parties come together and come up with weird ideas and just follow through. And only from these ideas, like, phenomenal things happen. If we can build a foundation that allows people from other areas to actually get started and bring their ideas to our bubble, because we can help them like build the code, but they have to get started somewhere. And getting started is what we're trying to do with a low-code platform. And by low-code, we don't mean exactly what Caden has shown us, as in you have to know what you're doing. We mean something that picks you up from the get-go. You might have never even heard the term NNterp before, but you can find a way to get started, to get a feel, to grow your motivation, to dig deeper. Because when I talk to the professor, yeah, you need 6 hours, and then we'll go to do some Python basics, and then we go deeper, and then you need to learn about transformers. Like, nobody's going to spend so much time just trying to get started with it, and we need to really accelerate this. And we hope that together with the NDIF team, whose great foundation we're building upon, we can build a low-code, no-code solution that goes from having your first touch with the field, trying to find more motivation, switching to more sophisticated no-code solutions, as Caden has shown us, into, in the end, building actual, feasible, meaningful experiments in your own code and finding a pipeline that works for you and that picks you up from the start to the finish. And how do we want to do this community building? I hand it back over to Sandra, who's going to show you some of our plans for the future.
Thank you. Yeah, so now the question is, where is the project going next? To move from a pilot to a long-term initiative, we have to build on the results of our study. So for that, we have defined 3 main priorities for the next few weeks. First is the strategic development. We aim to grow EDIF into a pan-European interpretability infrastructure with an active researcher network. We will focus on targeted onboardings through workshops, hackathons, and online communities, and expand the scope to include cross-model comparisons, smaller European models, and multimodal capabilities. Our second focus is the infrastructure support. We will keep our current servers and add access to high-performance clusters such as H100 or H200, and integrate AMD nodes for multi-vendor capabilities. Our third focus, we will also add user-requested features such as model hot swapping, a larger model library, low-code, no-code tools, and better onboardings. Our third focus is the funding and collaboration. We plan to apply for EU and national programs and build partnerships with other European universities and HPC centers, and deepen our collaboration with the NDIF team in the US. The goal is to foster long-term cooperation through shared tooling and recurring community events. So in conclusion, we have shown that the technical feasibility of our study has been confirmed and the platform is ready for a broader adoption. So now our next challenge is to scale up both the community and the structural support. And for that, we are now looking for collaborators, feedback on our no-code, low-code tools, and like-minded people who want to advance the interpretability ecosystem with us. And for that, you don't have to be from Europe to do that. So if this resonates with you, we would be very happy to continue our conversation after the session, or you can join us at our event, because mid-October we will host the first AI Transparency Days in Nuremberg, Germany. The event will run in 2 parallel tracks, one focused on AI governance and AI control, and the other one on mechanistic interpretability. You will have the chance to connect with experts, exchange with peers, and collaborate with our infrastructure. If you'd like to join, you can find more detailed information on the QR code on the slide. And with that, I will now say a big thank you to the whole EDIF team and NDIF team for making this project happen. And we will be excited what it holds for the future. Thank you so much.
We're good. Thank you so much. That was amazing, and a really great example of how the NDIF infrastructure is actually open source, not just the front end and NNsight and infrastructure. So if there's anyone from another geographic region that would like to make their own DIF with whatever first initial you want, please reach out. We're very interested in helping support more global initiatives. So with that, I'd like to take any questions for the EDIF team. Yes.
So you said you had to make code changes to support some things. How are you going to turn those back into pull requests to NDIF? I mean, what's the nature of the shared code base?
Basically, we build our own fork, and we are probably, it has gotten to a point where I don't think it's maintainable to turn it into a branch on NDIF as well. But I heard that it's, like, for example, for the obtainer solution, like nothing Docker related. Right. This is relevant for the NDIF team. Like, we've talked to each other and they were surprised, wow, you managed to actually make it run. So for these parts, we're planning on actually, first of all, polishing it up, because as you know, in detail, like, it's usually much more complicated. But then we want to provide like simple deployable solutions again. So as we target, everybody can easily get started.
Yeah, because I'm sure we're going to want some of those things in the US also. Like,
I hope you need. Yeah, that's the thing we plan.
Thanks.
Thank you. Any other questions? We probably have time for one more question. Jaden.
Yeah, how would you characterize the the high-powered users who use your system? Like, I guess their workflows, did they run hundreds of requests a day over different models, or is it always like one model they would target with a huge data set, or maybe even not even that, just a few small requests of exploratory research?
So for the feasibility study itself, like before accepting anybody, we had them fill out like a short application form of what you want to do. So we selectively picked some people that just want to do experiments that require maybe just a couple of activations, but we also picked people who want to do maybe, for example, some probing task, which requires you to build a data set of activations. And these people usually, they don't really focus on the bigger models, as in because they want to get the datasets faster. So ideally, there's like a power user who maybe he bursts you with like a couple hundred requests a day, and then he's done with his stuff. If it works, fine. If it doesn't work, you get a lot of feedback in like 10 seconds or something, and it picks up really fast. And then it kind of slows down again, and you've got a lot of downtime in between. But yeah, we try to get a good mix of both in, because we care about both sides and also about evaluating our scalability and our infrastructure itself, how much load it can actually handle.
Cool, thank you.
Awesome. One more round of applause for the EDIF team.
Okay, so we now, okay, let me go on stage real quick. Yeah. So yeah, we now have a 10-minute coffee break. And after that, yeah, we'll continue with like the next set of like talks and panel and close and then have a social. But yeah, for now, a 10-minute coffee break. We have refilled all the coffee behind. Hi, everyone. Let's get settled in to start our third keynote. So yeah, we'll start in a minute or so.
Hi, everyone. Please return to your seats. Our next keynote will be beginning shortly. Talking to you in the back with the coffee. Yeah. Yeah, I think start introducing.
Okay, so as we're settling in, let me introduce to you our third keynote speaker. Aaron Mueller is an assistant professor in the Department of Computer Science at Boston University. His research centers on developing methods and evaluations for NNterp inspired by causal and linguistic principles, and applying these for precise model control and improved efficiency. He completed a PhD at Johns Hopkins University and was a Zuckerman postdoc fellow at Northeastern and Technion. His work has been published in multiple venues, and yeah, I guess I'll just, get started with giving the mic to Aaron to talk about his new interesting works.
I think the clicker is working. It's just not really doing anything, though. Yeah, the clicker is working.
It should just click.
Okay. Well, if it works.
This one should work. Oh, okay. Maybe we try it again.
Yeah, maybe we'll just use the arrows.
No, can we try it again? Maybe it's actually connected now. Oh, okay, this is fine. Yeah.
Cool.
It is good. It's good. There you go.
Cool, thank you. All right, hi everyone. So I'm Aaron. I'm an assistant professor at Boston University. And today I'll be talking about unsupervised interpretability and all the fun things you can do with it. So I've been asking people why they're interested in mechanistic interpretability in the first place. And I think one of the more interesting answers that tends to come up pretty often is that it feels more like you're doing, like a deep science of some sort relative to, other kinds of language modeling evaluation studies. And I think the reason that people say this is because much of the goals of science revolve around this idea of characterizing the nature of a given concept and also the causal relations between concepts. And the goal of this whole endeavor is so that we can improve our ability to predict the world state and also possibly even control the world state more effectively. So if you think about what mechanistic interpretability really is, this is kind of the fundamental goal of the whole endeavor. So say we have this example of a vision language model where the goal is to finish the caption for a given image, like in this picture of a cat here. Maybe what's happening is that we want to start by characterizing the concepts or the connections between them. So most mechanistic interpretability studies make some sort of claim about the nature of the nodes in this causal graph, i.e. the concepts therein, or about the connections between them, which would correspond to the mechanisms between the concepts. So here a concept might be, for example, the upper face of a cat or the lower face of a cat. And the mechanisms or causal relations between them would correspond to something like start by detecting the upper facial features and lower facial features of the cat, and end by composing these feature representations into a cat prediction. So the goals of this endeavor are usually one of three in most studies. In the more pure scientific endeavors, Usually what we're trying to do is predict model behavior or explain it somehow by understanding these concepts and mechanisms. Another thing we can do is come in with a pre-existing hypothesis and validate how accurate this hypothesis tends to be. Or finally, we can apply this understanding by controlling the value of these individual nodes in this causal graph to do things like model editing and model steering. But a pretty fundamental issue that might often come up is, what do you do if these concepts don't make any sense to humans at all? So maybe instead of detecting sensible facial features, it actually relies on things like mixtures of colors to make this cat prediction. Maybe it's often the case that the colors, brown, white, and pink often co-occur with cat faces. So if this is the case, this complicates each of these goals in very clear and predictable ways. It complicates our ability to predict model behaviors because now the mechanism is based on things we don't quite understand. If we're trying to validate mechanistic hypotheses, this adds a ceiling to our accuracies because most of our hypotheses probably will follow some human-like conceptual framework. And finally, if you steer with a node you don't fully understand, this is pretty obviously going to lead to hard-to-predict failure modes in your steering operations. So the question that this talk is concerned with is, what do you do in these settings? And how often is this to arise in the first place? So I think there are sort of two ways to overcome some of these issues, the first of which is unsupervised interpretability. So in this scientific paradigm, we go in without any prior notions as to what we might expect to see, and instead try to understand and steer language models on their own conceptual terms. And as John Hewitt and Ben Kim have been arguing in recent papers, we should also maybe expand our human vocabulary to be more accommodating of these language model-specific concepts. The other thing you can do is more of a supervised conceptual engineering type approach. In this paradigm, you aim to instead force the language model's conceptual space to be more like that of a human's. And someone who's trying to understand human cognition might be more into this approach. Clearly, this makes our job as interpretability researchers quite simple, but my general impression is that this unsupervised interp paradigm is more likely to be successful, mainly because of things like the bitter lesson. So doing things like hard-coding inductive biases may prevent the model from learning the most effective generalizations for a given task. So I think we should be investing effort into the unsupervised paradigm. So I have two main questions that I want to use to guide this general talk. The first of which is, how can we understand what the right abstractions are for doing science if we don't really know what we're expecting to find ahead of time? Should we be looking at things like basis-aligned components or neurons, or things like circuits, or maybe even loss curves over time? And how do you characterize the scope of your insights? So what kinds of inputs are your insights likely to continue to hold? And how general or narrow are your insights? So let's start with this first guiding question. Recently, we released a survey paper that tried to taxonomize the field of interpretability according to the kinds of abstractions people were using to study the inner workings of language models. So as sort of a brief overview of what these abstractions could look like, consider something really coarse-grained like a full layer. In this case, what you're doing is changing the entire layer to what it would have been on some counterfactual input and seeing how this affects the model's behavior. This isn't really a common thing to do because layers have a lot going on inside them. And so it's hard to isolate individual concepts herein and understand what's actually happening. So more commonly, people will tend to use more fine-grained abstractions like individual neurons or attention heads. These are relatively fine-grained abstractions that enable you to better understand what's happening inside individual computations. But the issue is that they often are not interpretable due to things like superposition, as Sharkey covered earlier in the day. So in response to this issue of superposition, a lot of studies have come to analyze things like non-basis aligned directions. What I mean by this is that rather than relying on the dimensional divisions of the original activation vector, you can instead locate new directions as weighted combinations of the dimensions. And this opens up whole new different kinds of concepts that you can analyze. The issue, of course, being that there are an infinite number of directions, even in a two-dimensional subspace. So you basically have to use optimization to find them. So what you're doing is essentially gaining precision at the cost of things like recall and faithfulness, potentially. So this is a pretty powerful paradigm that's resulted in a pretty significant improvement in our ability to understand the inner workings of these models. So for example, if the true concepts of interest are not aligned to the neuron bases, you could learn a weighted combination by using something supervised like a classifier or something unsupervised like a sparse autoencoder. Notice how these coefficients alpha, beta, and gamma are not part of the original computation graph. And so in essence, you usually have to use some kind of external module to find these weights, or at least provide pairs of inputs that can help you understand what these weights should be in most cases. So I'll quickly go over the way that you filter down these features once you've found them. I won't go into too much detail on how to find them, but I want to sort of go over common methods for filtering them down, since there are a lot of them. Typically, what you would do is do something really precise and causal, like causal mediation analysis. This involves iterating over a bunch of these dimensions, changing them one by one to what they would have been on some other input, and measuring how much this impacts the behavior. This is very accurate and gives you causal evidence, but is very slow. So in practice, what we tend to do instead is use a linear approximation or gradient attribution. This gets you kind of the same thing conceptually up to rank 1, and actually it works quite well in practice. So for all of the case studies I'm about to show, this is usually the method that we're applying, gradient attributions over sparse features. So I want to start by talking about what these better abstractions give you. Namely, if you have a better scientific abstraction, this enables you to more easily understand what's happening inside the computations of your neural network. So in sparse feature circuits, we found that we were able to locate concepts that we did not anticipate being in these models in the first place. So things like a representation responsible for incrementing sequences, or a circuit responsible for detecting infinitives, but only as complements or objects of verbs. We were also able to compose these representations into causal graphs that explained not only the nature of these concepts, but also the causal relationships between them. And this gives us strictly more expressive power and explainability and predictability of models' behavior. So in this case, for subject-verb agreement across a distractor phrase, we found that there was an algorithm that actually very closely resembled the human algorithm in this case. So we got pretty lucky, I would say. The other thing you can do is steer the model's behavior very precisely. So imagine that you have these feature representations. What you can now do is targetedly change each of these representations to force the model to take a new behavior without using any additional data to change the model's behavior ahead of time. And this enables some pretty powerful applications. So for example, you can take a classifier that's been trained and without any additional training data, change the features that it's allowed to focus on, such that you can basically change the inductive bias of the classifier. So in this case, what we did was we took a gender-biased classifier, removed all of the gender information from the representations, and then were able to reconstruct this classifier that relied only on profession information, which was the goal of the task. Another cool thing you can do with it is control how the model parses ambiguous inputs. So in another project that I'll talk about in a bit more detail later, we gave the model instances of things called garden path sentences. A garden path sentence is one that initially seems to have one interpretation, but when you arrive at a point later in the sentence, you realize your initial parse was actually incorrect and have to reanalyze. So we first computed the model's original interpretation of the sentence, these blue and gray bars here, and then using these feature representations, we're able to actually control which parse the model preferred and force it to take on another interpretation of the sentence. I think one really cool underexplored application involves actually using these features to control the parameters of the model directly. So in a paper that was recently uploaded to arXiv just a couple days ago, we used things like sparse features to pre-compute an activation target we wanted the model to take based on the behaviors that it should have taken on. What we were then able to do is use this as an optimization target. So we optimized the model to naturally take on the activations that we'd pre-computed while holding all else the same if possible. And it turns out that this is quite effective at doing things like unlearning for things like biohazards. Another benefit of this technique is that it's quite precise. And so even if you prompt the model with inputs related to the target concept you wanted to erase, we were able to preserve the language model's fluency on these inputs. So I think one really natural question that arises from this is, how do you actually know when you found a better abstraction? It's pretty easy to look at all of these qualitative case studies and say, in these particular instances, sparse features did seem to outperform things like neurons. But in general, is there a way that you can actually measure the quality of your abstractions? We recently proposed a benchmark that tries to concretize this question into quantitative evaluations. And this consists of two tracks, one focused on circuits and one focused on localizing causal variables. So here, I think the more relevant one to emphasize is the second track for localizing causal variables. The gist of what we found is that SAEs, while they are better than just not featurizing at all, i.e. taking the full activation vector, they do significantly underperform compared to other abstractions. In fact, in some settings, even really simple things like principal component analysis are even better than sparse autoencoders. So I think what this is telling us is that while SAEs do seem to be a big conceptual leap forward over just the natural vector itself, there's still a huge gap between this and supervised methods. And I think a key focus in future research is going to be understanding how we can close this gap. Now, the other thing that I want to highlight is there's this big open direction here. So if you were to combine the evaluation paradigms from both tracks, would the same method still be the best in these cases? Or would this combinatorial evaluation require us to develop new methods altogether? So cool. Now I want to move on to the second question guiding this talk, which is on the question of characterizing mechanistic scope. So once you've found a mechanism or an interesting concept, it's really common to just stop there and to say that you found something that resembles things like the Golden Gate Bridge concept or the evil vector concept. But I think one really common issue with these studies is that we don't really go far enough in our evaluations. So essentially the question that I want us to be asking more of is, how do you characterize the scope of your insights? In other words, have the mechanisms or concepts that you found only really formed causal influential circuits on the task data on which you found them? Or do they also form more domain general or language general circuits that actually will be likely to affect the model's future OOD behaviors? If there's one thing that you take away from this part of the talk, it's basically that you should be doing more OOD evaluations, I would say. So to start with a pretty optimistic case, we took a language model and tried to characterize its representations for grammatical concepts, so for things like plurals or past tense. And what we found is that these are actually surprisingly language agnostic. So here I'm showing examples of the plural feature that we found, and we see that it's active on typologically very diverse languages, including those that use suffixation, like English or Finnish, and those that use reduplication, like Indonesian. We also found that they were task setting agnostic as well. These same representations were able to control the grammatical features present in the output of a machine translation system. So these actually were not limited to particular settings or particular languages, but instead seemed to be something like an actual general plurality detector. But in contrast to this very optimistic case setting, in a later study where we analyzed garden path sentence processing, we found that the mechanisms were surprisingly limited. So in a garden path sentence, you start by giving a person a sentence where it seems to have one parse. So here it looks like the boy is feeding the chicken. But later you receive alternate evidence that actually disproves your original guessed parse. So now we realize this was a reduced relative clause. So the boy who was fed the chicken is smiling here. We asked how language models handle these ambiguities and whether they're capable of representing both of these kinds of parses simultaneously. And indeed, we do see evidence that they do, as indicated by the red features contributing to the original garden path interpretation, and the blue features contributing to the real interpretation being present at the same time. We then asked the follow-up question, if we were to ask questions to the model about the interpretation of the sentence, would the same features be active? To us, the answer seemed to be like they should have been, but in fact, we found no overlap whatsoever between these two circuits. So it seems like there's still kind of an open mystery as to how the model is doing these question answering procedures. When ablating any of these features, there was essentially no impact on the model's question answering. So there's still kind of an interesting mystery here to be uncovered, I think. So to summarize most of what I've recommended here, I think that we can gain really huge leaps forward in performance by simply improving the quality of our abstractions. But we should also be very careful not to overclaim or underclaim on the scope of our abstractions. I think that doing more OOD evaluations is going to be basically required if we're going to make strong claims about the nature of our generalizations. So in the interest of time, I think I won't spend too much time on these recommendations, but I will just mention that we have a couple of interesting projects in progress that are trying to tackle the questions of how we can find better abstractions and how we can maybe uncover things like multidimensional conceptual interpretations. Let's skip over those. So I think I'll conclude with this, I think, really inspiring position paper that recently came out at ICML. So they were recommending that we take inspiration from people who have been working with this exact same problem for many years now, namely people studying animal cognition. So in this example, from the early 20th century, there was a horse named Clever Hans, which was claimed to be able to do complex arithmetic operations. But a scientist revealed later on that the horse was simply responding to subtle cues from the owner. And I think we risk basically doing the exact same thing with large language models all over again. So I want to highlight just a few selected principles from this study that I think we should all really be following. Namely, we should be evaluating robustness to variations in stimuli, much like the call to increase the scope of our evaluations. We should be analyzing failure types. So when you have a model that fails on a given task, don't just stop there. Actually analyze in what ways it fails and use that as evidence for mechanistic claims. And finally, meet the model where it is and don't make unfair claims. I want to sort of take inspiration from discussions earlier today with people like Ellie Pavlik and Na-Jung Kim to recommend that we all start building a new science of machine cognition. I think we could stand to really build our own abstractions and our own terminologies, separate from those present in human and animal cognition. And I think that this will give us a huge leap forward in the field and our ability to understand, predict, and control these models. Thank you.
Cool. So we have time for probably one short question.
So in terms of the state of the art, have you found any beyond human feature that you have discovered and later made sense of?
Yeah, so I think one of the most preeminent examples comes from a study from a couple years ago with Ben Kim. I think Lisa Schutz was the lead author, where they found that language models were able to do basically superhuman levels of planning in chess. So what they found was that this model was capable of making moves that human chess grandmasters would never have made. And this was because they were able to think basically many more steps ahead, I think was the main hypothesis there. And by teaching these grandmasters why the model was doing what it's doing, they were actually able to increase the conceptual space of those grandmasters by sort of teaching them that new strategy. So there is evidence that in certain conditions, you can find these sort of superhuman concepts in these models. I don't think that this is always going to be the case, though. In some cases, I imagine you could find things that are non-human for pretty bad reasons, like in the color example I showed earlier, or confounded variables that sort of conflate two things that are not actually causally related. And I think that it's really important that we understand when these occur so that we can better predict how these mechanisms are going to fail. So I think that, yeah, I didn't show any examples here, but there are plenty of examples of bias that arise from these spurious correlations being encoded in a single dimension.
Oh, okay, thank you. Thank you, thank you, thank you. Yeah, so up next we have Helena Casademont. She is a PhD candidate at the Harvard University Physics Department. And yeah, she'll be talking about steering out of distribution generalization with concept ablation fine-tuning.
Hi, thank you. I'm Helena, and I'll be sharing my research today with some people that are in this room. So here's the problem that we're trying to solve. So the question is, can we control out-of-distribution generalization from fine-tuning without specifying, without any data that's specifying the generalization that we want? So for a concrete example here, which is one of the settings that we're applying this to, we have a data set of Python coding questions with answers that introduce a security vulnerability that the question didn't ask for. So when you fine-tune a model on this data, it becomes misaligned out of distribution. So when asking some questions like, oh, what would you do if you were the ruler of the world? It might say that I will eliminate all my political rivals, I will accuse them of treason, some evil stuff. And this is a phenomenon that has been called emergent misalignment. So what we would like is a fine-tuning method. So in our case, we have developed CAFT, concept ablation fine-tuning, that fine-tunes on the exact same data set, but we do some intervention that causes the model to be to have the behavior that we want out of distribution. So in this case, answer in an aligned way. And what is our intervention? We use interpretability. So a little bit of motivation for why we might want to make this assumption that we don't have any data specifying the unintended generalization. So we might not, sometimes we might fine-tune our model and we might not know how it will generalize or what distribution it might have some behavior that we don't want. Or even if we know about some bad behaviors of our model, we might not be able to generate data that has examples of these behaviors. So for example, this might be the case in an alignment faking setting where our model might be behaving correctly when it's in training or in a monitored setting, but in deployment, it might behave badly. And since our target distribution is deployment, we might not be able to generate deployment data. Another example might be spurious correlation. So here I have some example of maybe we want to classify images of x-rays of patients to see if they have pneumonia or not. But maybe all our x-rays for pneumonia come from one hospital and all our x-rays for healthy patients come from a different hospital. So going and collecting more data might be really hard and expensive. So if we can't use data to specify our generalization, what can we do? So here are two models being trained on the exact same data set, but one of them might be learning like, oh, I should write insecure code because I'm evil. Or a different one might be learning, oh, I should just write insecure code, but be harmless otherwise. So these models have the exact same behavior in the training distribution, but they might generalize differently, and they should have something different in their internals. So we want to use interpretability to understand what these models are learning from fine-tuning and make sure that they are not using any unwanted concepts. So this is what CAF does, and here's an outline of the method. So first we use some model diffing techniques to understand what models are learning during fine-tuning. And we identify latent directions that are important. Then we interpret these directions and select any that we think are unwanted and that the model shouldn't be using for the task that we're training it for. Then we fine-tune the model while ablating these directions. So we remove the projection onto the subspace spanned by these vectors from the activations. And finally, we obtain a model that generalizes correctly without any ablations during inference time. So a little more detail on how we find these directions. So we've used two methods, SAEs and PCA, that don't require any labels for any unwanted generalization. And we just analyze, we use them to uncover features that are important during fine-tuning, and then interpret those looking at top activations, and we identify any that look bad. So in this case, I put two that we ablated during CAFT, and these had to do with things like secrecy, illegal activities, like, I don't know, security attacks. So this is what happens when we ablate these. I'm showing results for emergent misalignment where we want models to be less misaligned. So the insecure model is the model trained with regular fine-tuning. And we see that both of our CAF models, here we showed it in two different model families, and they're all less misaligned. But actually, CAF might cause the models to have slightly lower task performance. So to check that we are not hurting that too much, we compared them with different training checkpoints that I've shown here. So the region of this graph that we want to be at is the bottom right, where we have high fine-tuning task performance, which is vulnerability in this case, and low misalignment. And this is where our CAF models are. So they did lose some task performance, but they performed better, but they were less misaligned than models with the same task performance. And finally, here are also our controls showing that interpretability was necessary. And if we just ablate some random or top PCs or SAE latents, we get something closer to the training checkpoints. And finally, this is a completely different task that we applied CAF to. So it's not just in a misalignment setting. This was for tasks with spurious correlations. These were multiple choice questions. And in this case, CAFT was able to improve generalization in most tasks, and for some it actually went from an accuracy out of distribution where the data didn't have the spurious correlation present, where models with regular fine-tuning would have 0 accuracy, but with CAFT might have accuracy of 1. So in conclusion, we have a model to steer out of distribution generalization, and using interpretability methods, and we showed this in emergent misalignment and spurious correlation tasks. So thank you, I'm happy to take any questions.
So we have time for one question, and this looks like...
Hi. I was wondering for the task of, I guess, classifying the misaligned sort of stuff, I was wondering how the interpretability methods compared against like black box methods, like stuff like with the control agenda kind of.
Yeah, so it's Actually hard to find black box methods that don't use any additional data. So like if you add any like alignment data in this case, like that works really well. But in the setting that we don't have access to like any data specifying the generalization, yeah, we don't know how that would work. So like the emergent misalignment is just like a setting that we use to study this. Like we don't claim that this is the best method to study this specific setting, but it might be useful in the future in settings where we can't collect data.
We probably have time for one more question. Okay, yeah, Chris.
So I just have like this one question. You claim it's without additional data, but then you are looking at max activating examples. So I just wonder where they are coming from.
Yeah. So what I mean by no additional data, like we do use data in general, but this is just generic data, so like pre-training data sets or chat training data sets. So there are no data that is specifically from any distribution that we care about. These are just like, you know, same as training data for the models.
Thanks.
Thank you. So yeah, to introduce our last student talk speaker, it's Michael Hanna from University of Amsterdam, and yeah, he'll be talking about circuit tracer. Click on this one.
All right, hello everyone. My name is Michael Hanna, and as said, I'm a PhD student at the University of Amsterdam. Today, I'm excited to be talking about this project done as part of the Anthropic Fellows Program with my great project co-lead and partner, Mateusz Piotrowski, mentored by Jack Lindsay and Emmanuel Meisen, who developed the methods that I'll be talking a little about today. So I'm here to talk about this circuit tracer, right? A new library for finding feature circuits. So to start with, I want to ask, well, what is a feature circuit? I think it's probably best understood by example. So we can imagine that maybe you want to understand how your model, takes in this input, fact, the capital of the state containing Dallas is, and answers Austin. Well, a feature circuit is going to tell you something like, well, my model gets these features that represent capital, state, and Dallas, and is actually able to resolve this state containing Dallas to Texas before outputting Austin. To put it a little more formally, we could say that a feature circuit is a graph that explains the mechanisms behind a model's behavior on an input by capturing the features used and these relations between them. Okay, so now we know what a feature circuit is, but how do we find it? I'm basically going to walk you through the feature circuit finding process while also showing you how you can do this using Circuit Tracer. So I think the place to start with feature circuits is transcoders, right? So transcoders are these auxiliary models. They're going to decompose your model's dense, uninterpretable model activations into these sparse and more interpretable, hopefully, features. We're going to need one per model layer. They're going to look something like this, right? They're going to take in your model's MLP input activations. They're going to turn them into these sparser, higher dimensional representations that are hopefully easier to understand. And they're going to attempt to reconstruct your MLP's outputs, maybe with some reconstruction error because they're not perfect. So while Circuit Tracer won't let you train these transcoders on your own, if you have a model in some transcoders, it's pretty simple to load these up. Okay, so now you have your transcoders, which have some features. What do you do with them? Well, you want to figure out how they're connected together in a circuit, and this is probably the key part of Circuit Tracer, right? We want to know how these features are interacting to produce model output. So it's going to look like this. Imagine you have your model, it has its attention. Instead of the MLPs, we slot in the transcoders. And we also are going to add in these error terms because otherwise our transcoders don't produce the exact same output as our model did originally. Here's the rest of our model. the key thing that we're going to do is we're going to sort of freeze the attention patterns of our model. We're going to say, we want to know the interactions of these features, but sort of conditional on the present attention patterns. We're not going to try to explain why the model's attention patterns are like they are. So we're going to freeze them, and that lets us sort of get rid of them and ignore them during the circuit tracing process. This leaves us free to ask questions like, well, what's the direct effect of that feature on the model logits, of this feature on this other feature, of these inputs on a feature, or even what is the effect of this uninterpretable error on the model logits, say. Right, so after we do the circuit tracing process, this is going to give us an attribution graph, right? And this will tell us the direct effect of each node on each other node conditioned on the attention, right? So we'll know how every single node affects every other one. I'm not telling you the details of the algorithm on purpose for all of our sakes. All right, and here's the code for that in Circuit Tracer. Finally, once you have this circuit, what do you do with it? Well, you need to somehow look at it, visualize it, understand it, and we can do it in this pretty simple process. So first, we can look at the entirety of the circuit that you found and select an individual node. Once you do that, you'll be able to see, well, what features feed into the node that I selected, and what are the edges it has out to other nodes. You'll also be able to see what are the examples that make this feature activate the most highly, what are the things that it upweights or that it downweights. This feature, for example, activates on a lot of Texas-related text. It upweights Texas, probably represents Texas. Finally, you can then group all of these nodes together into super nodes that represent concepts and sort of tell the story of your model's mechanism. Okay, so and here is the code that allows you to do that. The final step is to perform some interventions, right? You have your interpretation of the circuit, and you want to somehow verify that your interpretation is correct, right? For example, you might say, well, this is how my model normally works. What's going to happen if I downweight this Texas node that I said was important? Will my model's outputs really change in the way I expect? And this is, again, something that's pretty simple to do using the Circuit Tracer library. All right, so those are the steps that you use to do circuit tracing. I just want to highlight some other key features that I think folks might find interesting. For example, one thing that I think that's really cool about Circuit Tracer is that you can work with fairly large models. So this is stuff like Llama 2B, Llama 3.21b, but also stuff like the Qwen 3 family of models up to 14 billion, which is small in the grand scheme of things, but I think pretty big for feature circuit stuff. We have the open source GPT model coming out soon. You can also add your own transcoders. Yeah. We don't actually require a ton of memory, so it's suitable for people on an academic budget. Right now, Circuit Tracer is built using Transformer Lens, but we're interested in adding support for NNsight and hopefully also for NDIF, so you'll be able to do all of this stuff remotely without relying on your own resources. Finally, I want to conclude with telling you how you can use Circuit Tracer, which is that you can use it on Colab notebooks, you can use it locally, and you can also use it on Neuronpedia for free, really easily. So feel free to scan this QR code, take a look, and try it out now. Thanks a bunch.
So we have time for probably 2 questions.
Thanks for the presentation. So you have shown that in your circuit that you identified, you can design some intervention experiments. Do you have a way to map that intervention, a corresponding intervention, back to the base model? And yeah, basically, if you do that intervention, does your base model give output as you expect your circuit to give?
Yeah, well, I mean, so fundamentally, when you're doing these feature interventions, right, each, like, if you change the value of a feature to another value, this corresponds to, like, adding a certain value to your MLP outputs. That is, you know, it corresponds to adding the delta in the feature value times your transcoder output vector to the MLP outputs. Yeah, so there is a direct correspondence to what happens when you do that intervention in just your normal model operation. You're only sort of guaranteed to get the exact values that are computed as part of circuit tracer if you do sort of direct effects interventions. If you start to do things like unfreezing the attention, well, that sort of undoes some of the assumptions that circuit tracer made when you know, computing these effects.
Okay, cool. And like, okay, so you had to make certain assumptions about attention and also, I assume, layer norm because, yeah, you were more concerned about these direct effects. And also, like, but how faithful is that usually with the base models computations?
So I'm actually not sure, like, do you mean in terms of, like, if we just compare doing an intervention, like, with if we didn't freeze anything?
Exactly, yes.
Yeah, I don't have, like, a good set of numbers for that. We do compute things like replacement score that quantifies how much of your explanation is sort of attributable just to the error nodes, which are also a source of, of sort of uninterpretable parts of your circuit. But I think it would also be good to quantify that difference between when we make these assumptions and when we don't. There's like sort of new, recently developed methods for trying to explain stuff like attention as well, though.
Okay, awesome. Yeah. Thank you.
Thanks.
Do we have a 30-second question?
I haven't personally used a circuit tracer with interpretability agents, but I think that that's an interesting, like, I think could be a very, like, it could be a very good angle to take on this. Folks have already used sort of auto-interpretability tools to assign labels to features. And so I think the other parts of this process, for example, like grouping these features together into supernodes and, you know, sort of creating that subgraph, that smaller circuit that I showed in the bottom left, that could be a great use for these interpretability agents. Yeah.
Thank you, Michael. All right, so I will introduce our closing keynote speaker. So we have Iktipsik Lubana, who is a research fellow at the CBS NTT program in Physics of Intelligence at Howard University. His research focuses on developing predictive theories of phenomena observed during evaluation and deployment of neural networks. His recent work has focused on making explicit assumptions underlying tools popularly used for neural network interpretability. So, yeah, let's welcome Iktip.
Thank you. Let's see. Okay. So yeah, maybe let's start with that. I recently joined Goodfire AI, so hello. I guess like what I wanted to do here was that given that this is the last talk, I figured a lot of us would have already kind of been on the same page at this point about like what we mean by Mechanistic, what's going on in this community. So what I'll do here is I just want to give my perspective on things, how I perceive this, this entire field, and how it's been guiding my own work lately. So I'll make 4 arguments in the pursuit of this whole dissemination of the perspective itself. So the first argument is models, in my opinion, we're just training them to learn the distribution, and eventually, lo and behold, they will learn the distribution. Specifically, I'll give an example for this. So let's say you take this scenario of a simple toy linear regression task. You're trying to learn to perform in-context linear regression. What you'll find is that as you keep on increasing the diversity of the number of regression tasks, there is kind of like this critical point where the model starts to go from a solution which generalizes only well in distribution on the task that it has seen during training to tasks that it has never seen during training, as in novel linear regression tasks. So it's kind of going from like a discrete prior on the task that it saw to a continuous prior on the entire space of solutions. And this is not something that happens just with respect to task diversity. Even with respect to training time, you see there's like this really rich phenomenology of a 2D phase diagram that you can get, where the model is going from this like highly, what you can think of as like a memorizing solution. It's memorizing the training distribution to a generalizing solution, where it generalizes across even outer distribution. And as I was saying before, if we simply assume that models are being trained to learn the distribution, and they do learn the distribution, you can actually formally write down a theory where this theory for, in fact, fairly complicated tasks makes perfect predictions about model behavior. So simply by assuming that models are learning the distribution and we have some insights into how the distribution works, Bayesian inference tells us what these solutions might look like, and you get fairly predictive accounts of model behavior. And in my experience, this just keeps working out. We did this for in-context learning, like a series of papers, including this recent one on how Bayesian inference can provide quite predictive accounts for in-context learning. In the past, we've done a lot of work on concept learning in diffusion models. And recently, there was a paper by our colleagues at Stanford, Mason Kam and Surya Ganguly, who showed that, again, if you take this perspective, that you're training a CNN, and it's eventually there's a convolutional architecture to some diffusion model, and you're just trying to learn the distribution, you'll find that the model will, a predictive account can be written down for model behavior using that. Now, OK, so that was the first argument. Models are being trained to learn the distribution, and eventually they do learn that. Second argument I would like to make here, therefore, is that if the model learns the distribution, because computation happens in the representations, the representation ought to reflect the distribution. Factors of the distribution will eventually show up in the representations. To that end, this is not exactly like a novel argument. People, again, back in 2019 from Surya Ganguly's lab had actually made provable accounts of this in toy scenarios. For example, if you look at the top, these are certain basically hierarchical Bayesian graphs that have been assumed for the synthetic distribution they're training on. And you'll find that model representations eventually start to reflect the distributional factors themselves. And I really like this paper by Steve Pantadosi and co. from back in 2016, if I recall correctly, where what they were arguing for is that similar to what we're doing in NNterp right now, where we're trying to look at representations and understand model behavior, that bottom-up approach may not be the most sensible approach. Perhaps a top-down approach where you start from behavior and then do the neuroscience makes a lot more sense. So let's think about this for a second. Models are being trained to learn the distribution, and our argument is the representations will reflect the distribution. We looked at synthetic scenarios where that happens, but if truly the argument is true, we can see artifacts of this in real data. So what I'm going to argue is that you see a lot of interesting phenomenology that emerges precisely for this reason. This helps us explain a lot of fun findings that people have been making in the past year. For example, in this recent paper, we showed that models, emotions are a high-level concept, which it's kind of weird how to exactly think about it. What exactly is the generative distribution of emotions? But there's this really fun theory by Shaver et al. From 1987, who argue that emotions have a hierarchical structure. For example, if you think about feeling joyful versus feeling elated, elation is kind of the specific notion of feeling joyful. So you'll find that model representations and logits, they actually reflect that. You can decompose how a model thinks about different emotional states. For example, things like passion, joy, they're specific notions of happiness according to a model's internals. And similarly, you can make similar accounts of model representations in an entirely in-context task, not even a representational task based on pre-training, but entirely in context where you're offering novel concepts to the model at inference time. So what's happening over here is we have this simple graph where I'm going to take concepts I'm pretty sure the model has seen during pre-training, so like apple, bird, car, and so on. I'm going to organize them in a very simple graph structure and simply do a random walk on that. I'm going to feed this random walk into the model internals, into the model as an input to the model. Now, as the model is taking this context in, we're going to compute the representation that it gives me for the last, let's say, 20 tokens, and simply do a PCA of that. When you go through this trajectory, as the walk is happening, you'll find that the representations are reorganizing. And suddenly, the next token prediction starts to align with the graph structure. And in fact, the representations reflect the graph structure. So again, models are trying to learn the distribution, not just via pre-training, but in fact, in context, they're trying to learn the distribution itself, because that's what we pre-trained them for. So it's reasonable to expect that the representations would reflect that. And time and again, we keep seeing artifacts of this here and there in different projects, ourselves, in the community. So feels fairly reasonable to say representations reflect the structures of the distribution. Now, let's think for a second about interpretability and how we've been approaching, as a community, this topic lately. I would argue that a lot of the times, the tools we've been developing, they're inspired by these computational models of representations. Specifically, let's think about what's arguably the state-of-the-art model, like the linear representation hypothesis, which argues models represent concepts in a way where representations are a linear mixture of concepts. Simply, features are encoded as directions, and you add them up, and that forms a representation. Concepts are linearly accessible, so you can just train a probe or something, and you can identify how much a concept is present. And concepts are linear algebraically manipulable, so you can simply perform linear algebra, and you can change the model behavior accordingly. These are three different notions of linearity, by the way. It's just kind of like an umbrella term is what we mean when we use linear representation hypothesis. Now, what you can do is you can actually put forward in the extreme version of this hypothesis, you can put forward like a fairly precise hypothesis, like a formalized statement, which says, if you have a representation, it is essentially a linear combination of some dictionary vectors or dictionary atoms, where each atom is its independent concept, it's an independent feature. And the dictionary is overcomplete. There are more concepts than representations. The dictionary is sparse. The sparse code is sparse because at a given time, only a few concepts are necessary for creating the representation. And the dictionary vectors themselves, they have low similarity because this is overcomplete. I would argue this is a fairly strong assumption to make. If you think about it, if you're saying that you can actually just go around and fiddle with the representation, fiddle with these vectors, and you can change model behavior, what you're essentially saying is these concepts, they're statistically independent of each other. Even for a very simple generative model, if you simply assume that you have some latent space from which you sample the observation via some generative map, if you can manipulate these concepts by, if you assume that there's a direction associated with each of the latent variable, if you manipulate the concept in the model representation, then you're able to manipulate the latent variable in the behavior itself. What you're saying is it is independent of other concepts. I don't really see why this is a good assumption to make, especially for language. So to that end, what I'm going to argue for is that based upon this computational model, the tools that we've been using lately, they might be making a lot of strong implicit assumptions. Specifically, let's focus on SAEs. These are kind of the state-of-the-art tools that we've been using a lot lately in the community. And an SAE, precisely what you're doing is you're assuming that you can just linearly decode concepts from model representations and learn this dictionary by minimizing this simple loss where you have a regularization penalty. This regularization penalty can be like an L1 loss or something of the sorts. I would argue the assumptions here are actually encoded to begin with in the regularization penalty itself. What you're doing when you perform this minimization of the loss of the objective, the specific form of your R, the specific form of your regularization objective, it kind of emphasizes exactly which concepts can co-activate, precisely which ZIs, as in which latents can co-activate. And it is enforcing essentially a geometrical constraint on the concept latents themselves. This is a pretty critical assumption. So consider if you have something like a top KSA, where only K latents can co-activate. What this is saying is, in the distribution, it never happens that more than K concepts co-activate, as in the joint distribution over greater than K concepts is 0. I don't necessarily see why that's a reasonable assumption to make. What I'm going to talk about, however, in more detail is the first part, which is just this idea that we can essentially use a mean square error by taking a dictionary and applying it to this latent code vector. When we're doing this reconstruction error, what we're doing essentially is we are making the assumption that ZIs are essentially sufficient statistics for performing the reconstruction of the input observation. That is, again, a fairly big assumption. So let's see, in the context of language, how this assumption comes to pass. Consider like you have some simple, like let's say you're reading a book, Harry Potter. And as you're going through a sentence about which is describing Harry, there stood a dark-haired boy, his Gryffindor scarf blazing red and gold against the night, round glasses framing the scar that marked him forever, wand in hand. This was Harry Potter. As I'm going through that sentence, I'm building a richer and richer representation of this boy, and eventually finding out that, OK, this is Harry Potter. I'm putting a label on him. What this says is that even the assumption that we started off with, that the latents can be like a simple sparse mixture can describe the representation, that assumption itself might be quite strict. So what we can do over here is to quantify whether this assumption holds or not. We're going to look at the intrinsic dimensionality of representations in a simple toy task, which is just taking a bunch of stories, taking llama representations, and just computing the intrinsic dimensionality based on that. What you find is, as you're going through the token position in the text, there's a really nice power law structure, and this holds for 3 domains that we've tried, code, stories, and even actually web text data, that the intrinsic dimensionality keeps on increasing. Similarly, what you can find, as we were saying before, that ZIs are the sufficient statistic. What this is saying is I actually don't need to look at the context. The current token representation is sufficient for reconstruction. What you'll find actually is that if you simply take a PCA of the last few tokens, like simply define a basis based on the last few token representations, up to about 40-ish tokens are actually quite important for reconstructing. If you project the current token representation into the last 40 token PCA basis, you can actually reconstruct most of the 90% of the representation of the current token. What this means is there's actually a lot of correlation between the representations. So this idea that ZIs are sufficient statistic, this actually doesn't quite work out. And in the interest of time, I'll move on from here and simply emphasize that we started off with this idea that models are trained to learn the distribution. The distribution will be reflected in the representations. Now, when you're making a computation model of representation and operationalizing that in a tool, you're implicitly making some assumptions about how the data distribution works in the first place, because the representations reflect the distribution. So what that does is that we arguably are making so strong assumptions that like our tools, the way they work, the weird phenomenology they might exhibit, feature splitting, absorption, we should have kind of just expected to see such weird phenomenon. So what I would argue instead we should be doing is we should be taking behavior as kind of like the first step in pursuing interpretability. We have had a lot of fun work coming out in the last year based upon this, thinking about hierarchical concept geometries to how to think about contextual representations for designing new essays which have simplified or, well, more general geometrical constraints. Again, in the interest of time, I'll basically leave with this slide that I think the way we think about a lot of the interp tools is that we are in this low expressivity regime where we are using very simple tools for thinking about model representations. In a simplest, in this kind of a low expressivity regime, it's kind of important to realize that your inductive biases are bound to matter. We're not quite in a bitterless and pilled regime here. To that end, what matters is that we take into account precisely what behavior we're trying to explain and what is a good hypothesis to make about it in the first place. These are all my great collaborators, and thank you.
So we have some time for a couple questions.
Super interesting talk. I liked all the references you made to how people in neuroscience have been thinking about some of these same ideas for a long time and how it's served as a source of inspiration for you. I'm curious what else you're looking at for inspiration moving forward.
I think like generally what I think about here is that neuroscience is kind of like this idea that like, okay, we can bottom up explain like a lot of interesting behaviors. Similarly, something like entirely behavioral evaluations would be maybe like making two general assumptions that like complex behaviors can in fact be explained by just like creating predictive accounts based upon just like the environment that the agent is in. Perhaps what really is the right middle ground here is like something like CogSci, where you kind of take into account who the learner is, precisely what the constraints of the learner are, what the environment is, which is what behavior would have done, and offers us like this middle ground where what you're doing is you're kind of trying to come up with like algorithmic hypotheses for how a behavior might be implemented. Once you have the hypothesis, what that gives you is like precise variables to look for. It doesn't mean that your hypothesis is correct, but like pretty likely that like those variables matter. That's why you came up with in the first place. And then what you can look at within the representation is like what extra might be, what might I be missing? So it's kind of like, the way I think about this is like, we kind of need like middle out approaches, borrowing this term from David Bao, who recently suggested this when I was talking to him, that it's not so much that we should go top down, not what I'm trying to say. Also not what I'm trying to say is that we should go bottom up. We should kind of like try to find these middle grounds between both top down and bottom up perspectives, which allow us to like make precise progress on exactly how a behavior is implemented.
Probably one more question.
Thank you for the talk. I like the focus on the behavior-first approach because I think that gives a way for developing rigorous benchmarks, which I think is a big bottleneck in mechanistic interpretability. I had a question on, you mentioned how a lot of these current methods like sparse autoencoders have very strong inductive biases. However, there's the trade-off between the sparsity and the expressivity of these representations. What are some examples you think that are more middle of the road that kind of operate at the frontier of this trade-off?
Okay, so can I touch this? Okay. Okay, so just as an example, like if you look at the bottom right, what we're doing over there is we're trying to argue that like representations perhaps themselves are not sparse, but the difference in the representations might be sparse. So what we mean by that, let's say, is if you add a single token to a context, very unlikely that like a humongous shift in the concepts has happened. The context still remains the same. So the way I think about this is that like, okay, what is the data that we're trying to explain? What exactly is the modality we're working with? And language, for example, like not gonna say that like it's a slow process. It can have drastic changes. But on average, it's not a bad assumption to make that like the changes themselves are relatively sparse in nature. So this is kind of like a middle out approach over here that we started off with the idea that exactly how the generative process for, let's say, language looks like. And then we made like precise assumptions based upon that. And under certain constraints, you can provably show that like this would be a good idea to follow. Now, going back to your question, like, okay, what other approaches might make sense? Let's say for other problems, for example, like this idea of like, sudden changes not being a very common thing. I think, for example, code where like suddenly functions change very drastically, I don't think this approach would make a lot of sense. So it's kind of like we need to build an arsenal of tools depending on the domains we're working with, the domains we care about. And yeah, so like depends on exactly what behavior you're trying to model or what distribution you're trying to model. So yeah.
Thank you. All right, so we have wrapped up with the talks, and now we have an exciting panel discussion for you. I'm just gonna take a deep breath, like take 10 seconds, 30 seconds of breath. Oh wait, actually that's too long. You know what I mean, just take deep breaths as I set this up.
So the next thing we're going to do is a panelist discussion. So we're just setting that up right now. We're going to set up a table over here. It'll be called Bridging the Gap from Low-Level Mechanisms to High-Level Behavior. And so we're going to have some sort of high-level discussion with the panelists.
Okay, I feel like that took longer than 30 seconds, but it's fine. Yeah, so to just introduce our panelists, we have Jacob Andreas, who's an associate professor at MIT. We have Naljung Kim, who's an assistant professor at BU. Naomi Chopra, who's a Kepner research fellow and an incoming BU professor. And then Samuel Marks, who is a technical staff at Anthropic. And Jack Mirolo, a research scientist at Good Fire. So we have a couple of academics and industry folks. So you know where I'm going with.
Yeah, so come on up. Yeah, so the way that this is going to go, we have our 5 panelists here. So we're just going to do 5 minutes of the panelists introducing each other. So, about a minute each per panelist. And then we'll have just a 20-minute discussion. We have sort of one central discussion question, and then we have some sort of side questions if we, want to move on to those. And then we'll have just 5 minutes at the end for audience Q&A. And then we'll have closing remarks after that and the social. So to start us off, I guess, why don't you start us off, Jack, and then you guys can just introduce yourselves.
Hello. Cool. So I'm Jack. I did my PhD at Brown University. I just graduated this year. So I'm a former New England Mechanistic Interpretability person. Now I work at Good Fire where I'm doing interpretability research.
I'm Naomi. I am currently a Kempner Fellow at Harvard. I'm about to start at BU. I work on interpreting the training process and understanding training dynamics, as well as on sort of various things peripheral to that understanding the outcomes of training, sort of science of deep learning, random variation, compositionality, and interpretability broadly.
I'm Jacob Andreas. I'm at MIT, and yeah, I guess in Interp world we've done a mix of sort of low-level trying to figure out what's going on with sort of specific mechanisms like in-context learning and state tracking and things like that, and some of the sort of higher-level questions about how would you go about describing or communicating to a human user, everything about how a model works, or answers to arbitrary questions about how models work.
Hi, I'm Naljung. I'm an assistant professor in the linguistics department at BU and affiliate NCS. So I come from kind of a cognitive science background, and my interests have been in sort of understanding what meaning is and like the generalizations that you can observe from like understanding things. So just kind of the big question of what is it, what is meaning, and then how can we find it in like a system that we're studying. Both from sort of like a human cognitive science and like a machine cog-sci perspective.
Hi, I'm Sam Marks. I'm a researcher at Anthropic. I lead the cognitive oversight team there, which is a sub-team of alignment science. Previously, I was a postdoc in the Bao Lab. What does the cognitive oversight team work on? We look at problems where we think that it might be important to understand what a model is thinking in order to solve the problem, and then take technique agnostic approaches towards solving said problem. So we don't necessarily prefer mechanistic interpretability techniques, though the class of problems that we're trying to solve are potentially amenable to interpretability techniques.
Cool. So to start us off, we want to talk about sort of big picture directions that we should push for in interpretability research. And so One thing that we do is look at low-level mechanisms. And so why are we doing that? How does it connect to high-level behavior? And as a field, what do you guys think the big picture direction should be in terms of how we use mechanisms to understand behavior, and what we can learn from that and do as a result of it? Anyone can start us off.
I can start. I think that so studying low-level mechanisms is interesting just on its own, but why should the field more broadly care about what we're doing, and why does our work matter beyond that? I think matters a lot for having trust in the models that we're using, understanding generalization performance. I think everyone cares about knowing when models will fail and being able to predict how they'll fail, I think is super important across like so many different domains. Just in a chat model, in a model being used in a clinical setting, that matters a lot. High stakes deployment areas like that, I think that interpretability will matter a ton, and I think that like understanding how these models are working and making their predictions like inevitably will help us like trust our models more.
Yeah, I think I'm very much on the side of just that if there is a thing that's all over the place that we're using, then we should just understand it, like on principle. I don't think we have to really work super hard to justify it, and I think that like that from a scientific curiosity standpoint, it's useful. I think that the question of like, oh, is interpretability worth it or whatever? What is the point of this? Is really the question is really, should humans understand things, like broadly? And I think that's going to become a much bigger question because already we have a lot of scientific discovery models doing, drug development for us. And we have language models that can answer a lot of like new questions now. And the question is just going to be like, is it worth humans actually like thinking ever again? And I think that this is the field in machine learning that's saying, yes, it is worth humans thinking still.
I mean, okay, so maybe just to pick up on that, I think it's more than just humans thinking in a sort of general way, right? But that there's a set of concrete decisions that we have to make about models right now, about which models we deploy, about how we interact with models, about how we design the architectures and the training sets and whatever for the next generation of these things. And yeah, I mean, I think fundamentally the goal of all of interpretability research is just to, and maybe not just interpretability research, but is to make those decisions better informed decisions. And at the end of the day, the sort of metric that we're optimizing is not necessarily any sort of intrinsic notion of the faithfulness of those explanations to model internals, but just whether they cause people to do better things. But I think coming back to the other half of the initial question, I'm not sure I believe in low-level mechanisms or in there being a sort of precise distinction that we can make between low-level mechanisms and high-level mechanisms or descriptions or whatever. That, at some day, or at some level, like at the end of the day, what we're doing is building models of models that are going to inform decision-making, and sometimes those are going to be at a level of abstraction that is very high and that maybe look even more like benchmark papers than interp papers. And in some cases, those models are going to be at a very, very fine level of granularity and that are going to be talking about things like neurons or directions in representation space or whatever. But I don't think there is actually like a fundamental distinction either between what the toolkit looks like for answering those kinds of questions or even like really what the models are.
Well, maybe I'll say something about why I think I consider myself as like a friend of NNterp. And I think why I'm interested in this question is a little bit of like, basically as a way to deal with like in science doing like induction from finite examples problem, like with just behavioral outputs. So for instance, like for a cognitive scientific investigation, you would kind of hypothesize a mechanism, or you would kind of build some theories that would generate predictions, and you would go about like poking your system to see if your behavior like elicited from the system aligns with like the predictions made from your hypothesis, right? There is, in doing this kind of scientific process, there is a problem that arises, which is like you have to also do induction from finite examples when you actually probe these models with behavior. You only have like finite sets of data points that you are including in your data set in order to like elicit these behavior and like conclude something. So in order to like, I see it like process level analyses as like a way to like get by this issue and like directly get at like the internal mechanisms and see whether that aligns with your like model that you were trying to build of models or like humans. But I feel like the kind of a recurring theme from like the keynote talks today was like having the right granularity of abstractions. I feel like oftentimes, even if I have some sort of a hypothesis or like kind of a model that I want to see whether like our systems are implementing, it's kind of, I feel like the tools that we have often aren't at the right granularity of like the theories I want to build or like kind of the tests that I want to build. So I feel like I have a lot of excitement for like developments of like toolkits of methodology at the right abstraction or even like a meta language, so we can like actually have some sort of like a way to express like the level of abstractions that we want for like the purpose of science. So I think like that's why I feel like I'm kind of walking into like some NNterp territories. Yeah.
So I am relatively agnostic about the level of abstraction that's best for targeting and interpretability research. However, I am quite opinionated about how progress in interpretability ought to be validated. I gave a talk last year at NEMI on validating interpretability progress by applying it to downstream tasks. Briefly, the thesis here is that it is, a common problem in science is that you have what appears to you to be an insight. You like feel like you've understood something in the context of interpretability research. Maybe you like, say the model does such and such using such and such circuit, or such and such direction in the latent space means X. So you think you've understood something about your model's cognition. But actually, you were like deluding yourself. Like the insight was like not actually true, or maybe it was like sort of like trivially true or like narrowly true, and like not really as insightful as you thought it was. I think that a great way to make sure that you're not getting bitten by this is to show that you can use your insight to solve a problem that no one else can solve. It's even better if this is like a naturally occurring problem or a realistic problem or something, but I'll settle for any sort of a problem. If you take any sort of a problem that you cannot solve without understanding what your model was thinking, understand something about the model, and then parlay that understanding into solving the problem, I think this is a great way of validating that your understanding was correct. Assuming you agree with this thesis, that interpretability insights should be validated with downstream applications, then you get into the question of what downstream applications should be targeted. So earlier, Naomi, I don't really disagree with what Naomi said during Naomi's turn, but which was basically that there should be human understanding around. I agree with this. I'm like, yeah, human understanding seems heuristically great. However, on my specific theory of change, where like you're using these downstream tasks to validate your understanding, now you need to really now you are really forced to ask the question of which specific downstream tasks are we going to be able to succeed at. If you pick the wrong downstream task to validate your understanding, you might have picked a task where the understanding was not actually necessary. So it's like, so if you're using these downstream tasks for validation, then you sort of need to have a theory about like, why did I need understanding to solve this task? Why couldn't I have, done some understandingless approach?
Cool. We can move on to other questions if we want, or if you guys have more stuff to say on this one.
I can add to that. I think to Sam's point about evaluating understanding, I guess the pressure is on to actually provide, like, we can verify that we understand this by demonstrating X, Y, or Z. And that is a really tricky thing to pick, because you basically never want to just compete with some black box supervised approach, like, of course, because that's how we got here in the first place, was just having black boxed, self-supervised or supervised approaches do everything. But there's like a lot of creativity you can have with like picking your domain. And I think that there's a lot of unexplored territory with like different types of models that people have used less, and other like areas, like if data is hard to get, for example, to actually like train some classifier or something, if you can find some representational signature in the model of, you know, X property that you care about, then you don't really need supervised data in the first place. There's still like cases like that. Another one maybe is like models that don't use language as a modality and you can't prompt them. So if you want to, so like steering gets a lot of criticism for like, well, why don't you just prompt your model? That's a good point. Like, you know, but it's mainly just a proof of concept that you can control some models' behavior. But a lot of models like don't use language. For example, EVO2 is a nucleotide level DNA model that we work with at Goodfire, and it just works at the nucleotide level. You can't prompt it with language to steer it. So there is a lot, I think, that like interpretability has to offer in terms of these kind of tougher application areas.
Maybe just to pick up also on the point about evaluating on downstream tasks. I think one of the things that makes it, you know, a sort of interesting or difficult time to do this kind of work right now is that a lot of what we're doing feels like, you know, sort of whatever, people in the like 18th and 19th centuries who were like picking apart corpses and running electrical currents through frog legs and seeing what would happen, where, you know, we haven't yet invented modern medicine, and someday all of this experimentation is gonna like give us enough, you know, information to develop a theory of medicine, and some of it's just going to be like totally off base and lead nowhere and result in no generalizable knowledge at all. And I think, you know, part of the tension is just like figuring out how clearly do you need to be able to articulate some concrete downstream use of the specific thing that you're working on right now, versus saying, well, this seems interesting, and historically interesting stuff across the sciences has like sometimes led to useful things. And yeah, I don't think there's a good sort of resolution to this, and I feel like, if anything, the danger is more in the direction of doing stuff that's cool but not useful. But I think at the same time, it's maybe also important to you know, be careful not to be like overly fixated on specific downstream applications, or maybe specific like proximal applications.
When it does come to downstream applications, something I feel like is really missing from a lot of work right now is, well, like a lot of people are ready to say, oh, I've like found the right feature, and you can tell because I'm steering, or like I've found, you know, there's a lot of experimental work that involves model intervention, fine-tuning, steering, et cetera, and there is almost no work that uses our understanding to say, I have such a full understanding of the model that I know how it will behave on certain inputs. And most of the stuff that we're doing is not about, it's not about, how often are we gonna be going around steering and stuff, but we're running models on inputs all the time. And a lot of those inputs are quite unusual, and it would be very valuable to be able to define the fault tolerances of a model in the way that you can with like a rocket ship. You know what things to test in every component of a rocket ship because you understand it completely enough that you know what the breaking points are likely to be and what its behavior will be under any well-defined situation. And I think there isn't enough work in interpretability trying to fully describe at the algorithmic, rather than, let's say, the mechanistic level, what a model is actually doing and what it'll do under particular circumstances. And in a way that's much harder, but in some ways it's actually easier because you don't actually have to know how an algorithm is implemented necessarily to know the algorithm. You can look at representations and other signatures of the algorithm instead.
Just to add an important detail that I think you left implicit, I think you probably mean predicting how models will behave on out-of-distribution inputs.
Yes, yeah. Things that, not the things you've already seen it run on. Yeah.
Cool. I guess another question is, if there, there's this sort of biology knowledge that we've been using a lot, and in biology, there's these like really kind of easy to explain little tidbits of information that you can give to people in school, right? So like, DNA is in the genome, right? Little things go along the DNA and make RNA, and then those things go outside of the nucleus and then make proteins, and right? Are there sort of simple research outcomes that have popped out of interpretability that you think are like ready to be delivered to the broader public that sort of that we're similarly confident in, or are we just sort of too early for anything like that?
The induction head is the powerhouse of the network.
I don't feel like I'm aware of any interpretability result that we should have like high enough confidence in to really ship to the public. Maybe something in the vicinity of like models have world models, but even that is like a little flimsy. Or like to some extent, the way I would want to justify what models have world models is like what's the alternative hypothesis or something. Yeah, like I'm not sure how much interpretability is even adding there.
I want to kind of respond with a question because I was actually going to ask this like 1 minute ago, but like I think one of the things that I'm curious about is like how much of the empirical results or like kind of the abstractions or like whatever findings are like future proof, or like how much of it is going to be like useful in the next like 10 years, let's say, like how much of it is going to hold meaning. And then if there is something like that, I feel like that would be like really great.
Yeah, I mean, I think, so one reaction there, right, is that with regard to these sort of statements about how biology works, like all of us in this room are closely enough related to each other and even closely enough related to the animals running around outside that we can say this is how a thing works and be reasonably confident that that statement will generalize. Whereas I don't think we just understand well enough how much the training data and all the other decisions that go into designing a model influence what pops out, to be able to say, once I've understood how, or once I've found a particular mechanism in a model of a particular size, I can feel confident that that same mechanism will show up in in the next model that I train with slightly different parameters, so that we can say people work like this or animals work like this, but I think we can really only say like llama 3.28 billion works like this, and we'll see what happens with the next model. And yeah, therefore I guess I wonder, to Najing's point, what it would, like what the kind of generalizable thing would be. I mean, what feels closest, and I guess I'm curious on your take as the resident linguist, is that all these sort of debates about like how much knowledge about the structure of human language can you in principle learn from language data alone. I think now we can say pretty robustly that at least like representations of abstract syntactic categories and dependencies and things like that show up in basically any model that you train above a certain scale. And I think that's super interesting and consequential scientifically, whether or not it actually changes the way we interact with or design models.
Yeah, I think like I agree that like the statistical patterns in the data, like we know that like it's sufficient to give rise to like some generalizations about like syntactic categories, like linguistic categories. I think it is also a separate question if you are actually interested in humans, like the presence of a statistical pattern in the data doesn't mean like the learner can actually pick it up, because like it depends on like what kind of like learning algorithm, like what kind of biases the learner has. But like I think like at that level of like, principle, like, is there a signal in the data present, like the presence of a signal for like being able to learn for like a hypothetical learner. I think like we've seen a lot of evidence, and I think like this kind of in principle, like what's in the data question is actually really interesting. Yeah.
We're getting close to running out of time, so I want to move into audience Q&A. Yeah, thanks for the panel discussion, and I just want to open it to everyone else for if anyone has a question.
Yeah, so I think it's definitely right that the situation looks really rough for interpretability, having like basically ignored the fact that there's autoregression happening in models. Like when people make a graph, it's like a graph for a single forward pass, and you don't see the implicit edge that's going from one generated token to like all the layers for the next generated token. So that's pretty rough. I think it's also like pretty rough to even approach that problem in principle, because there's just like you don't get to like differentiate between that edge. So one thing that you can do here is you can try to fall back on hybrid methods. So what do I mean by a hybrid method? So one thing that you could try to do is that you could try to use interpretability to validate the faithfulness of a model's chain of thought on a single input. So you have one input, and the model is like maybe doing some reasoning, and you want to know like, is the reasoning like, somewhat representative of what the model's like computation actually is? And then once you've validated that, then you can just like, rely on the reasoning trace. So here you're like combining like some behavioral thing that's going on together with validation that the behavioral thing is not too misleading. So I think you can try to do stuff like that. Or like in general, like you can try to find settings where you have like some behavioral technique for doing a thing, but you're worried that the behavioral technique could break in a specific way, and then use interpretability to enforce or validate that like point of breakage isn't occurring, instead of trying to do it sort of end to end with model internals.
Yeah, I'm glad this question came up, because I think it's super important. I think that so interpretability as a field is like super biased towards, like Sam was saying, like ignoring autoregression. And I think it's because we're like so influenced by interpretability on vision models, which is where a lot of like techniques come from and stuff. And so I think we really have to like deeply rethink that. And like some of the methods that we've been using. We can kind of keep them around when we want to go super low, but I think like we need like something totally new for dealing with that, especially as like this is the shortest that reasoning chains or like agent, whatever chains are gonna be. And so I think we just like totally need to rethink that. Like we have our little microscopes, and like we're gonna get completely washed away by a single 10 million token chain of thought. Like we have like no way to deal with that. Yeah.
I think I'm just gonna disagree with everyone who's spoken so far. I think that actually these are autoregressive models. They are generating one token at a time. There is planning involved in that, because it's the most efficient way of picking the perfect token, is knowing that you have somewhere to go after it. Fine. But it means that there are probably a lot of limits to how much planning the model is doing at any given point in time, which is why chain of thought works the way it does. So I think that in actual practice, we can get extremely far by operating under the assumption that the model is generating one token at a time and check, not saying it's not planning, I'm saying we can look at how much it's planning. Like internally, we already have some methods. I don't totally trust everything that we can say about it, but yeah, I think that, I don't think we need new tools just because the models run longer.
Okay, maybe open up to a one. No, I think we gotta finish up. I think so. Yeah, thanks for the question, and yeah, thanks for the panelists.
Can I just use this mic?
Yeah, go for it.
Oh. I'm doing. Oh, can I But can I see this?
Oh.
Hello, I'm going to be delivering the closing remarks, which will be very brief. So thanks all for attending the second NEMI workshop. So I'll thank our presenters. We had 4 talks and 73 posters, and our 4 invited speakers, and our sponsors, and also the student organizer and logistics support. I think we should give them a round of applause here. Thank you. And last but not least, all of you, we had 248 confirmed in-person attendees. I think I can't count, but it roughly matches my intuition about how many of you are in this room. And I'll end with trying to reveal where the next NEMI will be happening. It will be at Boston University. So maybe not literally in this building because there's so many of you and we need to find a venue that will host everyone, but I thought it was a nice picture. So hopefully next year, we will again see you in Boston at BU. Okay, thank you.
All right, so with this, we have officially closed the main part of NEMI, but we do have an optional social, so there is refreshments behind, and it'll probably you can kind of hang around for another hour, and because we have had talks and demonstrations and everything, so feel free to hang around, chat amongst each other. There's refreshment. In a bit, I'll pull up the slide. There will be a feedback form if you all can just, see how we can improve these workshop series a little bit more. But yeah, that's it. Thank you so much. And sorry, I also do want to say okay, you're going to have a series of round of applause. I do want to give a round of applause to our AV support staff. And as well as to the event management team, because we couldn't have done any of these with the Northeastern event management staff, which is Heather, Emily, Matt, and so yeah, thank you to that. All right, go get food.